Good day, everyone, and welcome to this webinar. And we are discussing this topic on the design of earth dams by finite element analysis using numerical modeling techniques. So I am your speaker for today. I'm Dr. Florante D. Pozo Jr. I am a full-time faculty of the FEU Institute of Technology. And before I work here in the Philippines, I work abroad in a Korean company. It is a construction company as a design engineer since 2018 until 2019 in different countries and different projects. So I started with them with a project named Shipyard and Dry Dock in the Sultanate of Oman. And with all of the projects that I work with them, we use different softwares. We use modeling techniques in analysis of different structures. So I applied it here in this topic, and we'll focus on the earth dams because it is susceptible to failure. So that is very easy to comprehend in terms of the analysis of the slope stability. Actually, what we are going to do here is to create our own preliminary design of an earth dam. Then we will do analysis, mostly based on the slope stability. If the preliminary design of the earth dam is safe in terms of slope stability. So with this, with the current, of course, in the current scenario in the construction industry, if you're going to do the design analysis, it is not most likely that you will just be using the hands-on or the manual calculation. Of course, we do that also. Part of the submission of the calculation reports of the different structures that we design will be that manual calculation. So using those empirical equations that we learned from our college years, and we apply it in the design analysis. So we do some checking, the same as through it if it is an RCD. Most likely because I am a water resource specialist, it is my master's degree program. So most of the projects that I am into are actually combined water analysis and geotechnical analysis. So when it comes to that part, in our department, I am doing the full analysis. So when part of the structure will be having um, structural design, so it will be given to the structural designers. Then we will collate all our calculation sheets. So that's the process of on how we do the calculation. So aside from those manual calculations that we prepare, part of the analysis is actually using different modeling techniques. So this is using the software. Most likely it is by finite element analysis. So what we will learn here, I will be showing you the software that we used in my previous projects. So this is a whole day webinar, and we will a lot of topics to be discussed. Of course, it is because of its restriction on time. So I just crop some of the major topics, and I will be discussing in the first part the theoretical discussion in terms of the slope stability, in terms of the dam design, which is actually an earth dam. So the failure of which is most likely in its materials because it is an earth dam. It is made of earth material, so the slope is the most critical. So of course there are other topics in it to be discussed, but we will focus here only on slope stability. You can still analyze using the software that I will be showing you in other types of analysis of an earth dam, like the seepage analysis. You can also use the software in terms of the earthquake analysis of hydraulic structures. For example, that's that of an earth dam. So it is all possible to come up because you cannot have it designed in one setting all of those analyses. So with this, we will be having our outline of the seminar. So first, we will just have a brief overview of the elements of dam engineering. What are those types of dams? Why we come up with an embankment dam? So just an overview. Of course, we have learned it partially during our college years in the subject. We have the hydraulics, you have designed the overturning and the resisting moments of dams. So we'll have just a review on it. And with that of the different types of dams, we will just select earth dams or some of the textbooks or references, they call it as an embankment dam, which is actually both the same. And take note also that the analysis that we are going to do here in the earth dams or in the stability analysis is also applicable to those of the structures, any structure or natural slopes that you are going to analyze in terms of the stability of its slope. So we will not the topic is not only limited to that of the earth dam. I will be give some other structures later in terms of how we can apply slope stability to other structures. So after that, with that of the overview, let us talk about the theoretical aspect of slope stability, which is actually the method of slices, which is part of the discussion in the geotechnical engineering subjects or in soil mechanics in the old curriculum. So I hope that you have learned it in the classroom, the method of slices, which is in which the original theory is the Swedish method of slices. But in the software, there are a lot of authors and exponents already who had been revising and making their own interpretation of how forces are acting in an earth material. So after that, because in the software is just very easy, especially if you are a civil engineer, it's very easy to compute, it's very easy to use the software, it's very easy to input the parameters, do the calculation using the software by finite element, the meshing and so on. So it is just very easy in to that part. But then in later on, if there are problems that may occur in terms of interpretation of the results that the software will be producing, it is only the civil engineers can interpret. If there are other people working in the department who are not civil engineers, they can actually process the design analysis using the software. But then in the interpretation and in the troubleshooting and in the redesign of, for example, if the slope stability fails, so what will be the decision that the civil engineer will make in terms of redesigning the whole structure. So that's how important civil engineering or civil engineers should be present in the department of the design. So because maybe some people may be thinking that because of the onset of this technology, the computer modeling and so on, that they don't need any more the civil engineers. The greatest part in that modeling and analysis is the last part, which is actually identifying the errors, identifying the meaning of the result, because the software will just give you a number. The meaning of it and how you are going to troubleshoot whatever the meaning of that figures or numbers that the computer software will be showing. So it is only the civil engineers can actually give their own analysis using engineering technical know-how. So we will be discussing all of the numerical modeling. So we'll focus only on slope stability. as I mentioned, the software can be used in the total design of an earth dam. So from slope stability, analyzing the materials if those are safe based on the factor of safety. It can also analyze the seepage analysis by water flux calculation, the flow nets, the different and pressures in the body of the dam and below the body, which is actually the foundation. It can also analyze the possible liquefaction. It can actually map which part will have a liquefaction after an earthquake event. So it is part of an earthquake analysis and so on. There's a lot of things that the software can do. So but this webinar will just have it focused only on slope stability. How we do the modeling of the dam, the input parameters we will discuss, then the material model, which is the more column analysis. When we talk of the more column analysis, it is more on the use of the unit weight, cohesion, and angle of internal friction. So the three of which, because in the seepage analysis, it's different modeling. So the material model is also different. And although you need only the input parameter as the permeability or the K value, but there are other parameters that is needed in the analysis, like the type of soil should be included. So the use of the last part is how we are going to use the software. So I'll be doing an actual demo of how we use the software, so using the earth dam. So we'll be having a preliminary design, then after which we will check if it fails or not. Then if it fails, so how are we going to change the design? Okay, so of course, in the civil engineering aspect, we always design a structure in which it will be both safe in the structural stability and the economic aspect of the structure. So we will be talking that one later once we do the modeling. Then if there is still time to model another structure, I'll be showing also the software, how powerful it is in terms of analyzing slope stability in other structures, like those of the sloping grounds on the side of the highway, those areas wherein it is potential for erosion and so on. So how we do analyze it. And the software, if it is a professional software, you can utilize any material in it. For example, if you do the repair, if there is an erosion, then you are making or proposing a repair method, or how you are going to stabilize the slope. Any material that will be applied on the surface or on the sloping surface can be modeled in the in the slope stability software. But the one that I will be showing you, as because the one, of course, this is a licensed software. So the one that is permitted by the company when I ask permission is only the student license. It is an educational license. You can use anytime the educational license. I'll be giving you the link of the software where you can download the educational software. But then there are limits into it. So other materials cannot be modeled. That's why I selected the earth dam, because the number of limits on the type of materials in the design can be catered in the educational license. So we'll be discussing all about that once we touch the discussion of the software later. So we'll start with that of the dam engineering. In our curriculum in the Philippine setup, the subjects that is being offered for the civil engineering program from first year to the terminal year, if you look at it, is somewhat biased to that of the structural part. So most likely when you think of a civil engineer or the program civil engineering, the people will always think that you will be designing high-rise building, the those of the buildings that you can see on the highway, both sides of the highway, were in the skyscrapers. So mostly that is the structural part. So they are thinking of a civil engineer that they are the structural engineers. So if we look into the specialization of civil engineering, we have different specializations, as we all know. As a civil engineer, we all know it. But other people who are not civil engineers, they always look at us as structural engineers. So, but we have water resources. We have geotechnical engineers. We have transportation engineers. We have the construction engineering and management specializations, and so on. So there are other sub specializations in it. So for those who design dams, who design the reservoir, who design those of the river embankments, the erosion potential areas, how they do the analysis and design are actually not the job of the structural engineers. So in my case that I work in a certain company that is specializing power plants and dry docks and shipyards, wherein most of our project, although it is both the onshore and offshore, but I am in charge mostly on the structures that are actually located or will be constructed on the sea area. So even the power plant. So those are always structures that is in contact with water and soil with the seabed. So it is a combination of the water resources analysis and geotechnical. So our the knowledge that we have for that of the water resources in the design of the water resources most likely is taken from the subject hydraulics only, which is very basic. So after that we don't have any more subject in terms of the design. For example, we studied before dam in terms of the overturning and resisting moments, overturning and resisting forces. Then you compute the factor of safety. Then you compute the resultant in the different cases. If there is water on the upstream, is there water on the downstream, is there an uplift pressure, and so on. So that is very general. But at the end of the course, at the end of your terminal year that you graduated civil engineering, if somebody will ask you to design a simple earth dam, a complete design of an earth dam, then give him the details of your design. Actually, we cannot give those specifics. But if somebody will ask us design a two-story residential building, for example, in your you graduated, all the people in your locality are very happy, and because you are a civil engineer, you pass the board exam, they will all most of the people there will be asking you to design for them their houses, mostly two-story building. It's very easy. You design the foundation up to the roof, if it is a rooftop or if it is a simple roof or whatever design specifications that they need. So it's just very easy. Why? Because from the very start, from statics, from strength of materials down to theory of structures to RCD to steel, even timber design, so that's the end. So what we did in the classroom is they will actually let you design those structures. So there are cases that they will ask, if the professor is very strict, they will be asking you to design a 5 to 10 story mid-rise building in their RCD steel. So that's the reason why we are inclined towards the structural engineering part. So in that case, when I proceed with my master's. So I learned a lot because the discussion in the master's degrees in water resources is very extensive in terms of analyzing now the different structure that has water, and mostly you cannot actually separate the fact that when there is water there is always soil. So it is both or a combination of the water resources and geotech. So combination of the principle of fluids, hydraulics, and the soil mechanics or the geotechnical engineering. So in my experience, teaching, because when I first work abroad, I work as a professor. I work as a professor in Oman and in Ethiopia for several years. And I am amazed with the curriculum that they have because it is a British pattern curriculum. Of course, Middle East is most likely towards they follow mostly the British standards. So their curriculum, the same as with Ethiopia because it is Africa. So their curriculum actually has this, aside from the RCD, aside from the steel design, they have this structure. If you are inclined into water resources and geotechnical engineering, there is two subjects for the design of structures, and that is called the hydraulic engineering. And that actually designs the different structures like dams, the irrigation structures, and other pertinent structures for irrigation, those with water. So those are hydraulic structures one and two. So river engineering and dam engineering. So all of the design is actually on canals. Of course, in the dam, if it is, for example, if it is a concrete, it is not only the dam itself that you're going to design. There's a lot of other pertinent structures if it is intended for irrigation, for electricity, for water distribution to the community, the design of the reservoir on how you are going to do the volume calculation, the design of the, if it is for irrigation, the design of canals, and if it is intended for electricity, there are turbine and so on. So you will be needing knowledge all about those things. So in other countries they have these specializations. So if you are going to pursue with a water resource specialization, so what you are going to enroll are actually subjects that is intended towards the output of designing water resources structures. So those are actually the subjects that I taught in in other countries. So that's why students there, after the end of the semester, when their output is actually the design, the full design of the dam or the full design of irrigation. So if it is for irrigation engineering subject, so they will be doing the whole irrigation, the design of the dam, and the design of the canals, the design of all of the pertinent structures. In river engineering, they have the spars and so many other. Of course, bridge engineering is different, but then those structures that is to protect the whole area in the bridge, it includes erosion control measures for the embankments and for the river. So those are actually subjects that we don't have here in the Philippines. But with the creation of the new CMO of the CHED, the 2018 curriculum, they are proposing for the specialization, and some schools had already applied it. In our school we have only two specializations that we offer: structural and water resources. So that's the reason why the students, if they are not into the structural part, they will be enrolling for other specializations. So, talking of the hydraulic structure subject, so when we talk of hydraulic structures, these are engineering construction designed and mechanically fit for managing and utilizing water resources. So that's why we talk here all about water. The reason why we construct the dam is actually to impound water in the reservoir area. So you have to manage the water resources that we have. So for, of course, for sustainability and for whatever purpose that it may serve. Most likely, for example, in the Philippines, we have a lot of dams. It serves the different areas, especially the Metro Manila area, for electricity, and at the same time the water for domestic purposes. So we have to utilize the water resources that we have for the best advantage of the human being and the environment. So there are a lot of discussion in terms of designing such kind of structure because it talks about its effect to the human being and to the environment. Take note that you are actually destructing, or the worst term for that is destroying the environment of that area, because you are going to flood the reservoir area, and flooding it will affect not only the trees, the whole environment, but also will affect those people living in that area. So anyway, that is another part of the story of that, the construction of those structure. But when we do hydraulic structures design, it always, of course, includes those aspects in how it affects the society, the environment, the economic part. So it should be, that's why there is what we call the environmental impact assessment. So it should be assessed the positive and the negative effects of the construction of the project. And the planners, the government will be weighing it in terms of the positive and the negative impact. If it will be beneficial to both the environment and the human being or the society. So since we are into the dam, so the dam, we will have just this basic definition that the dam is a barrier across flowing water. So most likely it is along the river you're going to block, because it is a barrier to that of the flowing water. That of course obstructs, directs, or retards the flow. So often creating a reservoir. So that's, there are basic dams like earth dams. Of course, for earth dams, it is just small. It is not intended for electricity or for the multi-purpose. So it is just used for a single purpose. So concrete dam is intended for a multi-purpose project. So sometimes it will cater all of the its objectives for electricity, for water consumption, for irrigation, and other purposes that it may serve. So that is the dam. So the reservoir that it will be create, for example, this in this picture, this is your dam, and you have there the reservoir. If you can see, it is a large area. If really, if it needs if you are going to compute the volume, then you will be needing the total area of this. Of course, you are going to, as a designer, you are going to design the height of the water in this dam, which is the flooding, the flooding height of your dam, because you will not be designing it. Actually, if for concrete dams, you have to design it with that of the analysis of overtopping, because it may occur, especially during the time of typhoons or heavy rainfall. So, but for earth dams, of course, it is not allowed to overtop, but it, because it will destroy the whole of the dam. So in designing the area of the reservoir based on the volume requirement, so you have, there are a lot of equations that can be used for the computation of your volume, total volume that is needed. Of course, the total volume that you are going to stack in here in the reservoir depends on the water requirement in the output area. For example, for electricity, if it will be producing electricity all throughout the 24 hours, so how much water that it needs to operate the turbine. And if it is intended for domestic purposes, so how much volume of water is needed for the total area that it will be serving. So for example, it is the whole of Metro Manila, how many population, and requirement of water per capita. So it could be a liter per capita. So you'll be computing that one. And because you are going to have it reserved in that area, so you are going to stock the water in the reservoir. So there are allotted period, how many months that you are going to stock the water, that it will be safe in terms of its purpose. So for example, during summer months, if you're going to make stock of that water. So you're going to compute the water requirement times the per capita, but of course you are going to include now the number of months that you are going, that it intends to stock the water in the reservoir. So this is a picture of um, potential river in which they had created the dam here. Then you have there the reserve, the whole of the water coming here, and it is you have the guide bands. These are actually the structures that is being designed in the hydraulic structure subjects. Then if it is intended towards the for irrigation, so you have the canal headworks to be designed. Then it is now this area going to the canal. So of course there are roads and there are other pertinent structures. So diversion works also can be part of the design. If, for example, there are cases wherein you are going, there is over flood in the reservoir area wherein there is uh, excess water that needs to be diverted, so to avoid flooding in the both sides of the rivers or after it flows out to the dam. So when we talk of dam, it actually differs from all other major hydraulic structures. So of course, this is the biggest structure in all of the hydraulic structures. So in every dam, whether it is a large or a small or concrete or made of earth materials, it is always quite unique. You cannot always say that you are just going to by design in another area of this dam, since I'm also creating a new dam which is almost the same structure specifications, that you can have it copied paste to that area. Of course it's not, because of number one is the topography, second the flow parameters of the river, the the different parameters also, or the properties of the foundation of the soil foundation, and so on, and sometimes its purpose. So you have to make sure that you have to analyze each of the dam that you are going to design. For example, you are designing more than one dam, so it is always different from each other. So parameters and required properties should always be checked. So dams do not have a structural lifespan. They may, however, have a notional life for accounting purposes, because of course when we talk of the economic part, or the the cost of the project and its ROI. So we have to a lot of or specify its lifespan, but not totally. When we talk of, when we say it's 50 years, it's the 50 years of its structure. It's only intended for the accounting purposes. So dam engineering draws together a range of discipline, especially if it is a multi-purpose dam. So constructing a dam for the purpose of electricity needs electrical engineers. So mechanical engineers also for the construction of the turbines and other parts of the electrification that will be constructed in the dam. Of course those requirements from the electrical, mechanical, and other engineering fields should be discussed all together, and the one that will be designing the dam should incorporate those requirements. So that's why it draws together different disciplines. It is not only for the field of engineering, because take note that before the construction of the dam, even though it has, for example, it is a government project, then it has been analyzed already, and expert on environment, on the impact assessment. They are there already. They assess the water quality. They assess the aquatic resources, its effect on it, the air quality, and other environmental factors that may be affected. So those are different disciplines also. But then after that, there are also other people that will be created in a group. So a group should be created in terms of talking with the people that will be affected also. So those are about the field on sociology, and so on. So there are those people that are expert in negotiating, so other of course, they are going to negotiate those people that will be affected to the construction of the structure, one of which is actually their land, then their houses that will be flooded and will be part of the reservoir area. So there are a lot of problems that may arise on that. That's why it actually includes a range of discipline, not only in the field of civil engineering. Of course, the technical part will be the engineering part, and there are other parts that should have been considered. So, for example, I work with the irrigation authority for a year in my province. So we constructed the main canal. So of course there are a lot of problems in terms of how we are going to although the design is coming from the national offices, when you plot it in the province, especially if it is in the far-flung barangay, the people there will not be allowing to construct the main canal if it is too large. It is almost 2 meter width of the main canal, then it will be passing through their lands. They will not be allowing that. And if the negotiators will not success in convincing them, so there should be a redesign of that. So those are just at the process of how the construction of those structures progress. So sometimes there will be delayed because if it is still under negotiation, so you have to stop the project until such time that a redesign or the new design will be approved again, and so on. So this is just a picture again of your the whole dam. Then you have your spillway. Then you have your reservoir. Of course, the minor structures should also be included in the design, no? If it is intended for whatever purpose. So dam is a solid barrier constructed at a suit location. That's the reason why the first requirement is actually the to select the best location of the dam. So it is across a river valley, and the purpose of which is to store a flowing water. So most likely it is on those rivers that has a continuous flow all throughout the year. That's why the flow characteristics of the river should also be studied from January to December to identify which month in which the flow is very minimal, very low, and of course that's the time that you are going to maximize the storage. So the purpose of storing water is actually based on the different objectives, which I already mentioned. Number one is hydropower. So for, of course, this is for concrete dams already, that when you construct a dam, you maximize its use. And if it is possible to generate electricity, then much better. Then another one is irrigation. Of course, this is only for small dams that is being constructed mostly on the far-flung barangays that are considered to be agricultural area to irrigate, because most areas, even in my province in Samar, so still majority of the areas, the agricultural areas in our town or the whole province are still looking into or waiting for the natural irrigation, which is just the rain. So it is not yet fully irrigated the whole province, but they are at present constructing new dams and irrigation facilities. So that's one of its objective. The third one is for domestic consumption. So of course, for example, in Metro Manila, so there are a lot of dams that is servicing Metro Manila. So another structure that is being built and servicing it is actually the water treatment plants, because of course water from the dams should be treated, and after which it will be distributed to the whole community for domestic consumption. So there are also dams that is the main purpose only is to control the flooding in the area. So there are other for navigational facilities also, and of course it is for tourism purposes. It can be for fisheries development. Take note that the downstream side of the dam will be having less water. So on the upstream wherein you have the reservoir, the government should develop fisheries development projects intended for the residents of the area also. So if it is a large dam, they have it used for tourism purposes, and even nowadays there are a lot of the watershed area that they utilize it as a tourism's destination. So those are the different objectives on why we are actually constructing dams. So here are the classification of dams. We have the embankment or the earth dam as we know it, and you also have the concrete dams. Concrete dams is actually common to us. We have the arc dam, the gravity dam, the buttress dam, and there are sub classifications also of dam based on its type. So for the embankment and earth dams, we have the dams with facing, dams with cores. It could be a silt or clay core or asphaltic concrete. So if it is made of a concrete facing or it is made of an asphaltic concrete facing. So meaning it depends on the type of material for the earth. So we will discuss specific on the earth dams. So this is a cross section of the dam. Of course, the upstream is vertical, so it is concrete in nature, or the material is concrete, because you cannot construct an earth dam that is vertical, that has a vertical slope. So that's why one of its failure is actually the slope. The reason why we design it based on stability analysis, because it's very weak in terms of the stabilizing the slope, especially if the material is very weak. So you have the crest, you have here the two, wherein this is the point wherein we take moment for overturning and resisting. Then this is the heel. Of course, we design for the freeboard. So we'll just discuss later on some of the specific in terms of the different requirements for crest, how we do the design for crest, the freeboard. No? Of course, the first parameter that you're going to compute is the mean water level here. Of course, you have the maximum flooding, and which one will you be using in your design, in which flood height. So you have the normal water level also. So this is the upstream side. You have the spillway inside the dam, and this is your downstream side. So that is the whole structure of the dam. It is just the basic elements of the dam. So since we are into the earth or embankment dams, so let us discuss what are the embankment dams. So embankment dams are defined as the dams constructed of natural material. So that's the basic term for it. It is made of an earth or natural materials. So it is excavated or obtained from the vicinity of the dam site. The purpose of which is actually for economic purposes. So if you are going to construct an earth dam or an embankment dam, make sure that the location in which you are going to extract the materials to be used, the earth material to be used, should be near the dam site. So the first type of embankment or earth dam is earth fill or earthen embankments. So from the word earth fill, it should be made of earth materials. So this may be classified as dam use compacted soil. So that is the earth materials that I am referring to. So for constructing the bulk of the dam volume. So there is a homogeneous earth dam, so it is made of one type of soil. So constructed primarily of selected engineering soils. Of course, in the design of the dam in terms of soil stability, the main parameters of which using the Moore column analysis is the unit weight, cohesion, and angle of internal friction. That's why you are going to select the best engineering soil that is actually will fit to that of the requirement in terms of factor of safety. And of course, in the construction, it should be compacted uniformly and intensively in the relatively thin layers. There are a lot of codes and standards in terms of this. Of course, the quality assurance will be telling the construction department on the minimum or the maximum layer of compaction. So it should be controlled moisture content also because you are going to measure the compaction value. Once the first layer is approved by the QA, so you can proceed. Because you cannot, it is not that of the requirement that when you construct a dam, you just fill in all of the cross section, the total volume of the dam. So it's not it. So you are going to place by layers and compact it. So here are some of the types of the earth dams or the earth fill dams. So you have there four figures. So the first one in this area, which is the upper left, is homogeneous with two drain. So homogeneous, so it is one type of soil, but then there is one part here that is called the two drain. So it is made of granular materials, gravels or boulders that is placed in the two of the dam. The purpose of this is to protect the two and redirecting the seepage. So of course, the seepage will start from this interaction point of the upstream slope and the water here, and you're going to draw a parabolic point. So it is the phreatic line. So it, of course, it is in another topic. It's in the seepage analysis. So just to redirect to avoid redirecting the seepage towards the two because this is the most weakest point. That's why we have this as the point of moment. So that is one of the purpose. So it is just explained in there. So you can model this homogeneous with a two drain in the software. The second picture is letter B, upper right. It is homogeneous. It is still homogeneous structure of an earth dam, but this time it has a chimney drain and a horizontal blanket. So the same material for these two drain, you can have it in this way. You have the chimney drain and you also have your horizontal, this one, blanket. So the purpose also of this is to minimize the seepage. So the figure letter C in the lower left, it is a zone with clay core, and it is from the figure B, but it also utilizes a core membrane made of clay. So it is of different materials. So there are, of course, it has an effect in terms of its slope stability and seepage. It is always the point because sometimes if it has a different because in what's this in the C page we talk about permeability, so it's better to have different types of materials in the whole of the structure, but of course it will incur additional cost. That's why you have to consider also. Then the fourth one is from C, but then they also added a zone, another zone with earth and rock fill. So from the clay, they have another zone here, but it is made of rock. But the large volume of which is actually made of soil. That's why it is an earthen fill type of embankment dam. The second one is rock fill. There are only two types of embankment and earth dams. So that is an earth fill and rock fill. So when we talk of earth fill, so majority of the whole structure, whether it is homogeneous or zoned or there is a core, so, but the majority of the total volume of materials in the total volume of materials is made of earth. So the opposite of that is a rock fill material is made of rock fill material. So in this type of dam, there is an impervious core of compacted earth fill. So in the center, so you have there the or a slender concrete or bituminous membrane. But the bulk of the dam is made of gravels, coarse rocks, or boulders. That's why it is called the rock fill embankment. So you have there your figure A. It is a vertical clay core and drains. Then you have made of course rock fill. Then you have there the core at the center. So in the letter B, the inclined the core is inclined, made of clay, and you have the drains. Then you also have this in letter C, lower left. It is an upstream deck with asphaltic or concrete membrane and drains. You have the drains here. Then Part of the soil stabilization here is to lay a concrete or an asphaltic material. Then in figure letter D, you have the asphaltic membrane with grains, but the asphaltic membrane is actually at the center. So whatever design that the designer wish to adapt, so of course we will have to make it or do the analysis in terms of slope stability. So let us check later if what we can do in the model that we will be having in the using the software, using these different types of dam. So both in the earth fill and rock fill, we will be using different materials later. So just a sample of an earth dam. So you have there the earth dam in this side. Mostly you cannot even see that it is already an earth dam because the crest, they utilize sometimes the crest as a highway. So, but then if you can see, there are slope protection also made of boulders or gravels on the sloping side, on the upstream side. So this is just also an example of an earth dam, a simple earth dam, which is intended just to store water, maybe for irrigating his or her farm area. So the source, we don't know if it is where it is coming. As long that there is a source of water, then they just create a reservoir, a small reservoir. So the dam in there is actually this sloping part. So of course it does not need a thorough analysis in in this structure because it is intended only for a small project, just to irrigate the maybe just to irrigate the farm. So this is the top view of that earth dam. So the owner has this farm, so he has made this just a simple reservoir. So this is a dam in Ambuklao. The name of the dam is Ambuklao Dam in Benguet. So for example, if the structure of course you will not be analyzing the slope stability of a concrete dam because the cohesion of concrete is very high, so meaning it will not fail in terms because you can even pour concrete which is vertical. So but then the software can be used in analyzing the other parts which is actually the natural slope. So for example, this part and this part, so if you have the properties of this the materials, then you can use the software in analyzing the slope stability. We also have this the San Roque Dam in Pangasinan. So just a view. So if it is a concrete structure, you can see on the different sides, it is made of natural slopes and materials. So the software can also be used in analyzing the slope stability of both sides. So this is in Isabela, the Magat Dam. So embankment dams has actually a lot of advantages. So of course, we cannot deny the fact that it also has a disadvantage. That's the reason why we have to design it because of that of the disadvantage. So here are the following major aspect in terms of the advantage of an embankment dam. These are suitable for river valleys of any type. So it can be constructed at any river valley, whether it is a steep or a wide valley. Can adapt to a broad range of foundation because it is not that heavy. And unlike if it is a concrete and it is a big structure, of course you will not be constructing an earth dam which is too much big, similar to that of the concrete, because it has only its limitation. So therefore, it can adapt to the different types of foundation condition. So ranging from whether it is a good rock or even a permeable soil type, just the normal or the natural river bed can be utilized as its foundation. So it uses naturally available material. So it is friendly in terms of the environment. So relatively less cost. And of course, since it has a disadvantage, that's the reason why we do the full design, the full analysis of which. So it may be said that they have greater susceptibility to damage than concrete dams. So due to the possibility of getting washed out. during an overtopping. That's why it should not be designed. So the one that will be doing the analysis of the maximum flood height should be careful in analyzing the total flood height of water. So in terms of that, because it is susceptible to that of the damage, so the material should be checked. So this material that will be used for the dam, that the soil properties should be checked, and it should be analyzed well in terms of slope stability. So that's the reason why we are going to design the earth dam in terms of slope stability, because of this disadvantage that is susceptible to that of the damage. So the dam will not overturn because of this condition, and it is actually, we all know this in our hydraulic subject. We need that the resultant force shall falls within the base. Of course, it would be safe unless the resultant is found outside the base of the dam. So that is the first condition. So to prevent tension at the upstream phase and excessive compression at the downstream phase, the dam cross section is usually designed so that the resultant falls within the middle third at all elevation of the cross section. That's why the base, we divide it into three, and we locate the position of the resultant. If you still remember that calculation, so it should be within the best, and the best location of the resultant should be at the middle point of the base, but it could not. It's very difficult, especially when you are changing the dimension of your dam. So the best way is just to locate it within the middle third. So good impervious foundation are essential. Of course, the foundation, we are looking only into the analysis of the slope stability. But of course, in the total design of dam, the design of the foundation should always be considered, because it carry, of course, we know the role of the foundation, as it carries the total structure above it. So it has a mass that lends an atmosphere of permanence, stability, and safety. So therefore, it talks about the unit weight. So the more heavy the structure, so it is based on the unit weight of the earth material that will be used, will also have an effect to that of the stability and safety of the structure. Take note that the total weight of the dam, or the weight of the dam, is part of the resisting forces or the resisting moments. Later we will be having, I have a presentation in terms of how you analyze using the method of slices. So here are some of the, of course, this is not part of the engineering aspect, or the civil engineering part, the technical side of the structure design. But we have also to consider the different effects in terms of the environment, social, economical, political concerns. So that's the reason why you have to investigate in a team, in the construction, in the planning. Of course, we as civil engineers will always be part of the team. But then, as mentioned in the previous slides, it actually draws a different range of disciplines. So there should be one that will be looking into the environmental effect of the project that you're going to, whether you have done it or you have designed it very well, the slope stability is very safe, seepage analysis are within the tolerable limits, the foundation design is all well calculated, and everything are actually in terms of the structural stability, it is all safe. But then we have always to consider the environmental part of which is considering the environmental impact assessment. So if it really damages the whole of the environment, and there are a lot of negative impacts for air, for water, for those of the aquatic resources, and for the different plants all of the area, so you have also to consider the result of the EIA study. Another one is the social concerns. So you have also to listen to the concerns of the people that will be affected of the whole area. So economic part, so of course it will always be part of the analysis. So the total cost and its return of investment. So are there any political concerns in the area? So of course there will always, if it is a large project, there will always be the especially if it is under the government, even the contracting side, there will always be political issues in it, and so many things about those things. So you have to consider all of these sectors. So we have always to consider these five core values. It should be equity. Of course, we look into the economic side of the project, and it should be sustainable, then efficient in terms of its purpose and objective. And another one is participatory decision making, as it needs approval also from the different agencies, from the people that will be affected, and lot of agencies. Then, of course, the last core value is accountability. So all people involved should be accountable. Not only, of course, the engineers that do the design, but then there are a lot of aspects that should be considered. So here are the seven strategy priorities for water resource development. This is the number one, and actually the most important among those priority, which is actually to gain public acceptance. So that's the reason why you have the social investigation. You have to address social concerns because we need the acceptance of the people in that area. As regards, even it is not a dam, it is not a hydraulic structure. Even other projects from the government, if it is a non-government, and so on, it is good thing to check first if the people is accepting the project. There is a public acceptance in the construction of the project, and if they really accept that, it will actually result to that of a success in terms of the utilization of a certain structure or of a certain project. So that's why there are information drive to educate the people why you are going to construct the dam, why it is intended there, even though it will, because the people there, the laymen, will not understand the technical side of the structure. So how it is being, because they will always think of how it will destroy the environment, always the negative part of it. It will destroy their properties, it will actually destroy their land, and especially if the people will be relocated because of the flooding of the area in the reservoir area. So those should be considered. Then there should be options. So, of course, there are a lot of options in a feasibility study. So, you have to assess the best option in it. Then, you are going to address if there are existing dams in the area. Sustain rivers and livelihood. That's the reason why I mentioned in the previous slides that the reservoir area could be utilized by the government for tourism or for fishery development activities to sustain those livelihoods in the downstream side. Recognize entitlements and share benefits. And because, of course, the people will be looking into what they will get after they will be relocated, and so on. So there are a lot of negotiations in it. So another one is ensure compliance. We always have to ensure, especially for environmental policies, because we have to make sure that it is sustainable and at the same time it is not destroying the environment. So here are some of the criteria, because of course when we design later, when we do the analysis, that the first one are the different criteria in our design. So one of which is the location. So how we are going to locate the best position or the best site for the dam all throughout, because when we do the survey all throughout the river, so we are going to check some parameters, some tests, some analysis, and so on. So here are some of the consideration. The dam should be as near as possible to the area to be served. Of course, it is the most important. Why? Because of the conveyance cost. If it is for irrigation, so you need to construct a very lengthy main canal towards the area. So there's a lot of consideration in terms of water losses and other losses, and it should be minimized. So it should be near as possible to the area to be served. So foundation area should be impervious and should be able to support the weight of the dam. That's why analysis also of the different properties of the river bed or the different soil below the or in the area should also be analyzed. The topography of the dam and reservoir site should permit maximum storage of water at minimum cost. So that's why you have to, based on the aerial maps and different maps that you'll be utilizing, designing now the reservoir should be carefully studied in terms of maximizing the storage, and at the same time the cost is being minimized. So we also have the materials of construction that should be considered. It should be available in sufficient quantity and of good quality. So why good quality in here? Because it is made of earth dam. And the slope stability and its factor of safety is actually basing its value will always based on the quality of the earth material that will be used. So it should be available and the quantity should be sufficient enough for the construction of the dam. Another one is the value of property and land, which will be submerged by the reservoirs to be as small as possible because you are going to pay for those lands. And if there are negotiations that other people will not actually agree with some of the conditions, so another set of negotiation consideration should be take into consideration if they, maybe some people will be asking additional price for their lands, and there are other requirements if they will be relocated. There are other freebies like in the relocation site there should be a full house to be constructed for them, and so on. So the cost of relocating roads, buildings, if there is, should be as small as possible. So, because of course, if you are going to construct dams, there will be roads that should be constructed. The cost of stream diversion and dewatering the site should be as small as possible. So this is also to be considered in the costing. So the stream diversion and its dewatering, transportation facilities and accessibility of the site. So most of the dams that are being constructed, if it is still in the remote area, the first thing to construct is actually the access roads. So it's part of the cost should that's why it should be considered in that analysis. Availability of suitable sites for construction equipment and camps, especially if it is a big project. So of course the people, the equipment should be located on site. So here are the dam site investigations. What we need here? Of course, this is the preliminary stage wherein you are going to investigate first. Number one is the general planning and preparation of location maps. So you should have the team should have those location maps. So the whole stretch of the river should be mapped, and there should be proposals as to the location of the different structures. Then you also have the hydrologic investigation. So of course, this is the collection and analysis of the flow, the precipitation records. Of course, if that is very far from the existing Pag-asa station, there should be a precipitation measurement to that of the area for all throughout the year. So there are a lot of investigation in terms of these parameters. So estimation also of flood peaks. There should be records of the different height of floods that occur in the area. Determination of spillway capacity and groundwater studies are very important. So topo survey, of course, because you need the exact topography of the whole area, so you'll be requesting surveyors to conduct a detailed topographic survey. So detailed survey for areas proposed for the different structure, spillway, the diversion tunnels, outlet, powerhouses. So from the location map that is being proposed, so you have to conduct different or the detailed topographic survey. Another one is surface geologic investigation. So you have to identify boundary of this deposits overburden if they're the different layers of the soil. So there should be boring that will be conducted to identify the characteristics and the structure of the bedrocks. So we have to identify also that the fault zone. So all geologic parameters should be considered in this investigation. So subsurface or foundation exploration, which is actually the boring activities. So you have there the sinking open pits, drilling holes. You can drive a shaft or drifts just to get samples and should be analyzed in the laboratory. Seismic surveys. At present, we have the seismic maps already, so we can identify the seismic activities in a certain area, or we can get it from the different agencies that caters into the seismic records. Then construction material survey should also be part. So there should be a team that will look into consideration the availability of the material that will be used and the testing of the material. So what are the properties and or parameters that will be tested in the laboratory. So here is the stages. I just actually present it in here. So it is just a diagram of the planning and implementation process. If you can see the strategic planning project in the field reconnaissance itself, it's actually took a minimum of 3 years and even go further beyond that of the number of years of the project that you can have the a continuous reconnaissance survey in terms of mapping, survey, and data collection. But for the initial planning, you actually will be having a total of 3 years minimum to get the maps, to get that. Because if you are going to conduct the, for example, the precipitation, the rainfall data, you need the total year data. So it will incur that number of periods of months just for that parameter alone. So, but of course, during the investigation, a series of or other activities are also being done, like the soil analysis, the foundation analysis, and other surveys. Then, once you have all the data, you will proceed with that or the feasibility study and the report. And most likely, the time span is from 1 year to 3 years. So it will take time to finally decide which among the options is the best. So the next one is the dam site evaluation and the reservoir site evaluation. It is made through and through. Then confirmation of the type of dam, whether you're going to use a concrete dam or an earth dam. So it took actually from 2 to 4 years. Then phase two is the dam site investigation because you already had selected and confirmed the type of the dam. So you are going to finalize based on the final site investigation. Then you can proceed with the dam design. The dam design is actually within just a minimum of 1 year. It's just very easy if you have all the data that is required. Then construction, of course, it will took 2 to 6 years. It depends on the type of structure. So, but you are going to have a feedbacking route here if there is some problems in terms of the different checking, like for example, foundation check. So if it really fails in the design analysis, so you are going to go back if during the construction, during the excavation, and hauling of some other parameters. So there are other parameters to be considered in the design, or if it needs revisions in it. So I think that's it for the introductory part of this webinar. So it is just a brief background of dam engineering and how we do the or the different types of the dams. So we will just proceed with the different topics that is being outlined for this webinar. So let's proceed to the next topic. And this time, let us discuss first what is embankment dams, or actually, it is known to most of us as an earth dam, but in some literatures, they call it as an embankment. So both embankment dams and earth dams are just the same. So we are actually into an analysis of an earth dam, although designing a dam is not just like you just have it simulated by slope stability analysis and seepage analysis, or by dynamic analysis. There are a lot to be considered in terms of its full design. So in here, it is just an 8 hour to 9 hour webinar, and we will just be tackling some of the basics and brief review of the theory and principles of how we are going to design embankment dams. Although the main focus in the later part is to use simulations using softwares for finite element analysis. So what I can show to you is actually the simulation on how we are going to analyze slope stability. But of course, before that, we are going to have a brief review of what is slope stability, what are the principles behind, what are the theories behind the slope stability analysis, and what we call the more column analysis. Because what is important there is to understand the input parameters. It is not just having it inputted all the values. Of course, other people, even not a civil engineer, can operate the software, but understanding the parameters that you are going to input and the output analysis or the result view could only be analyzed by civil engineers. And that's the role of our profession. So although there are a lot of softwares nowadays in terms of simulation, in terms of analysis. So aside from that, we'll also have a sample of a seepage analysis. So those are just part. So let us have it analyzed later. I hope you will have a full grasp of the what is slope stability and seepage analysis in embankment dams. So when we talk of earth dams, it is actually called the ancient type of embankment. Those are, and the purpose of which, if it is an earth dam, is of course to impound water. But when we talk of earth dams, it is just of small area. So unlike nowadays, of course, we just seldom see earth dams in big or in a large area, because it is made of concrete already, because the focus or the objective is not just by impounding water alone for irrigation, but it is intended also for electricity, for domestic water supply, for irrigation, and it is already a multi-purpose dam. So, of course, earth dams cannot carry the volume of water that is required for that kind of purpose. So, those are ancient embankments. As we know that from the word earth dams, it is built of natural materials only. So those are just made of rocks or soil, or a mixture of which, with, of course, in the ancient time, they used primitive equipment. Nowadays, we also have already our heavy equipment to prepare the layering of the earth dams. So another one is it can be easily constructed on earth foundation because of course the weight itself is not that heavy, unlike concrete. If you can see high or very the height of the dams exceeds like 30 meters or even more. So the weight itself that resists the pressure of the water or the hydraulic pressure on the upstream dam. So it is the weight can actually is the one that will resist to, of course, avoid the overturning effect. So for earth dam, it is not that heavy, so the foundation can still be the same as is, whatever the natural ground can be that, or if it is not enough, you can change, but it's still it is of earth materials also. But the problem is that embankment are more susceptible to failure because of the material itself. Number one is actually the slope. So if you fail for the design of the slope, of course, it will end up to failure. Then another one is for the seepage because there will be seepage through the body of the dam. Aside from the seepage below the foundation, there is seepage that will pass through the body of the dam. Unlike for concrete, it will not be having problem in terms of seepage through its body because it is concrete. So what they are going to analyze is the seepage below the structure, and they will just design some other measures, its foundation, and adding sheet piles or whatever measures that they can include in the design to minimize the pressure of seepage. So those are what we call the earth dams. So that's why in earth dams, we have to analyze number one, its slope stability. So the design of slope should be okay. So later we will be having, of course, there are already codes, there are already standards published by different organizations in terms of their suggestions in terms of slope, which depends on the height of the dam, or sometimes it depends on the height of the maximum flood height of water in the upstream. And some parameters to be considered. So it is just very easy. So you just follow those standards, you just follow the suggestions from the different standards. Then after that, you can have your own analysis. Then if it fails, then go back again, then redesign or change some of its parameters, mostly the slope if it fails in the slope. So for seepage, if it fails, mostly it could be of the material type, or it could be you have to add some other measures to strengthen the structure. So there are two types of earth dams or embankment dams. So number one is what we call the earth fill or the earth dams. The second one is the rock fill or the earth rock dams. So from the terminologies, it's just very easy to comprehend what is an earth filled dam and a rock filled dam. So from an earth filled dam, it is mostly made of earth materials, which are mostly soil. So from the rock filled earth dams, it is made of rocks. But of course, it is not that of the perfect homogeneous or 100% rock or 100% earth fill. So there are consideration to be checked also because as I have mentioned, you have to analyze the slope stability and seepage. So in that sense, in slope stability, what matters most is actually from the more column analysis are the input parameters in terms of unit weight, then the cohesion and angle of internal friction. And for the seepage, you have the permeability. With those parameters alone, you have to consider the materials itself. If from the unit weight you need a heavy material that can resist all the pressures that is acting on the dam. So for permeability, you are of course you will be needing much compaction and so on. So for rock fill, of course it is made of a granular materials. So pores are much bigger compared to that of the earth fill. And compacting it is not that easy because there are still voids. So what you're going to do is to mix it with earth fill to fill in the void. So those are just an example. So but later you can have it analyzed using the software or some of the theoretical analysis. So let's try to discuss what is an earth-fill dam. So it is a bulk of mass in an earth-fill dam consists of soil. So of course, the comparison to explain the earth fill is actually the rock fill dam, which is consist of rock materials. So it depends on the method of construction. So either it is a roll field or a hydraulic field. Of course, it's not anymore part of the analysis whether because it is part of the method of construction later. So in the simulation, it doesn't require for an input whether it is a rolled field or a hydraulic field dam. So, but let us define what is a rolled field dam. So, the embankment is constructed in successive and mechanically compacted layers. So, of course, having in some, I don't have an experience of constructing the whole of an earth dam. What I have is actually those temporary dams, like the temporary cover dams, when we construct the different structures in the Sultanate of Oman, like the shipyard and the dry dock, the power plant also, because some structures are situated or located already in the sea area. So surrounded by waters. So to block the waters while you are going to excavate for foundation, you have to construct temporary dams. And we call that one as the temporary cover dams. So after 3 months or 4 months after the excavation and after the construction of the foundation, then we will demolish again the dam. But of course the same procedure in terms of construction, although that it's just there is the level of difficulty because it is already in the sea area is much difficult compared to that of you are just blocking a river. So in there, the same procedure with this of the rolled field, you are going to lay the materials layer by layer, then of course compaction, then the suitable materials are transported from barrow pits. The most important thing to consider in terms of earth dam is that the material should be located near the structure because cost there, of course, in terms of transportation, hauling, and so on, there is a cost incurred in there. So you have to consider always that one. But the problem is if the nearby areas, if all the materials has been tested and it fails with that of the different analysis, so of course it is of different issue in terms of costing. So in the feasibility study, whether it will pass or not, the most important thing is the materials will pass the requirement, especially in terms of the seepage and the exit gradient. Because in the different theories in seepage and exit gradient analysis, the material is very important. So in the exit gradient, there are tolerable limits and per type of material. So we have to be careful in terms of what material we are going to use. So that is the rolled field dam because in the earth material, you are just going to have it from the take it from the barrow pit, then transport it to your location, then have it layer by layer. Of course, in terms of layer, there are a lot of standards to be considered. Maybe some of you will be asking how many thickness and so on. Some they use as 300 to 500 millimeter or point 0.3 by or point 0.5 meters, then have it compacted. So it depends on the method of construction. So from the method statement as approved by the Quality Assurance Department. So the hydraulic fill dam, the materials are excavated. So after the excavation, it is transported and placed by a hydraulic fill method. So it is just actually the method of placing the material. The material mixed with water at barrow pit and is pumped into the flumes. So and going to the area wherein you are going to construct now the dam. So the rolled field earth dam types can be of homogeneous, can also be of zone embankment type, or a diaphragm type. From the first one, which is homogeneous, so meaning the material is just one material. So it is of the homogeneous type. So another one is the zone embankment. The zone embankment is, from the word alone, zone, there are different zones in it. So it could be there are core, there are outer and inner layers. So meaning the material, the whole of the earth dam is not anymore homogeneous because you are going to place different materials, some of which are finer, then other one are granular. Then the third one is the diaphragm type. And when we talk of the diaphragm type, there is a diaphragm wall in the center. I think I have the pictures in it, so I'll show you later. Oh, this one. So this is the homogeneous embankment type. So if you can see, the whole of the earth dam is of homogeneous material. So take note of this. For this figure A on the top portion, it is a purely homogeneous dam because you can see all of the materials are just the same. So below that is of course your impervious foundation. So there is one line there which is your seepage. So it is the phreatic line. So the topmost line of seepage from, of course it is, I think I have later slides in terms of how you're going to do the seepage. But using the software that I will be showing to you later, it is just very easy because the software will do the drawing of the phreatic, of this line, the topmost seepage line. It is very important because it will help the software analyze which part is saturated and which part is dry. So take note that you're going to input the dry unit weight of the material. But then if you're just going to analyze separately the slope stability in this figure, the software doesn't know whether the area is dry or saturated. But then when you simultaneously analyze the cross section both with the seepage and the slope stability, the software now will determine that this part below this line is already saturated and the upper part is dry. So anyway, we will have it discussed later in the analysis of slope stability and seepage. So the lower part is the modified homogeneous dam. Why? Because if you are having this kind of seepage line wherein it will go through, because seepage will either be going outside in this area from the 2 to this approximate h over 3. What is h? H is the height of water, and divide it by 3, so it is somewhere here. And take note that in an embankment dam, or in the dam design in general, this area, which is the 2 area, is the weakest point. That's why we take moment at this point. We take the moment for the overturning and the resisting moment. So what that's why we have to take care of this. And even especially for the earth material or earth dams, this is also very weak, in which the pressure of the seepage will go through in this area. So this part will be washed away easily. So what they are going to do is to include a filter below this, or in this area, so below the structure. So you have there the drainage filter. Using now the software, you can view there that the seepage is redirected towards this line, so not anymore at the 2. So that is just one technique of diverting the seepage. So another one, here we are, the zoned embankment. The zone embankment type, as patterned from the word zoned, so you have the different zones. So you have here the pervious outer zone, then you have there the impervious central core, so which is another zone. So it could be of the same material, so it can be divided by another transition filter. So another material, so it has different permeability. Number one purpose of having those is could be to reduce the pressure of seepage. So it can be. That's why in analyzing different type of embankments, of course, in this compared to that of the homogeneous, this one will incur higher cost because of the material of the different materials in this cross section. But then if those of the homogeneous will fail to that of the requirement, so zone embankment could be one of the solution. So you just have it there. Of course, if you can see there are slope protection. The same with the homogeneous type. You have always to include slope protections on both sides, not only on the upstream, because this is also in the downstream side, this is also prone to failure because of the effect of rain or typhoons, or that will in which the rain or the wind will blow this area. So that's why there are so many protection materials that can be placed. So for the diaphragm type, you can see there is a core here, a core membrane, which is called to be the diaphragm. So it is directed to that of the previous foundation. So the and of course below that one is your bedrock or the impervious foundation. So then you also have the slope protection and so on. So this one is of different materials of the diaphragm. So we'll try later if we can have a sample of the diaphragm in the diaphragm type of embankment dam in the simulation. So here is a feature of an earth dam. This is just a general feature of the whole of the cross section of an earth dam. You can see there the top width. So, because these are actually most of these features, you're going to decide or come up first with the preliminary design. So based on, of course, the first thing in mind is where can I get the value of the top width? Where can I get the freeboard, right? The base width, the slope, and so on. As mentioned earlier, I will be showing to you some of the standards from the different codes and guides from different literatures in terms of coming up with the preliminary design of your earth dam. So you have the freeboard, then of course the you will compute the maximum flood. So it is based on the total volume of water required to be impounded. It is for if it is for irrigation, you have to compute the water requirement of the whole area, and it should be during the summer period wherein you are going to impound much water because of the less rainfall event. So it depends on what's the purpose of impounding the water here. So of course for concrete structures, concrete dams for a multi-purpose, there is another kind of calculation because you are going to calculate the requirement for irrigation, electricity, domestic supply, and so on. So you also have here the wave protection, which is actually the slope protection to protect this area, the upstream side. So these are the zone embankment because you have the upstream shell, you have the downstream shell, then you have the transition filters, then you have the core membrane. So this is your hill, this is your two. You can have there this two drain or the filter, the two filter, or you can have it as the horizontal one, and so on. So you have the foundation, and of course it should be laid in the impervious stratum. So that is just the basic features of an earth dam. So what are the key elements of the embankment dams? So number one is the foundation. So that's why there is another type of analysis in the embankment dam, which is the foundation analysis. So it is in the geotechnical part of the study. So analyzing the bearing capacity, the uplift pressure, analyzing the stress, the strain of the soil. So of course it is not, we did not include it here already in our discussion because it is of a different topic, and it's a lengthy topic to consider because it is both the foundation design of an embankment dam and the analysis of the soil behavior. Then we also have the core or the membrane. So those are with that of the non-homogeneous type. So the primary purpose of the core membrane is to hold back free water. So it is on the seepage effect. So you have the shell. The purpose of the shell is to provide structural support for the core and to distribute the loads over the foundation. So you have the upstream and the downstream shell. So this is also true to that of the non-homogeneous. So, what are the causes of failure of embankment? As mentioned in the definition of the embankment dams or earth dams, we have the we have mentioned that it is prone to failure, susceptible to failure because of course the material itself. So here are the causes of failure. Number one is hydraulic failures. So second one is on the seepage failures. And the third one is the failure on the structure or the structural failure itself. So let us discuss this one by one. So hydraulic failures includes the overtapping. So of course if the earth dam is not designed for overtapping. Unlike for concrete, if there is an excess water, so you can just open the gates or just have it overtop on the structure, so it is just okay. But take note that if it is an earth dam, it is of course made of an earth material. If you overtop it, the whole dam will be washed out. So it could be a failure in the design of the maximum flood height in the upstream dam. So of course we have to protect the structure in terms of overtapping. So another one is erosion of the upstream phase. So in this, because of the effect of the this pressure of the water and the waves, because it is not of steady, there are winds in this area, so it is moving. That's why in all of the design of the earth dam, so you have always to include the protection here, the wave protection, the slope protection, and so on. So another one is the cracking due to frost action. Of course, it is for those areas which has frost action. So let's move to the second one, the gully formation. So this one, due to the effect of this rain. That's why I had mentioned earlier that you have to protect both the upstream and the downstream side in terms of slope protection. Of course, in some areas I've seen, if example, they had just constructed earth dams for their farm area, for their farmlands, which is just small. So they just actually construct small earth dam. So what they did as the protection is they use sandbags. So they just put sand inside the bags, then have it layered on the slopes. So it is just similar to that of the rip wrapping. Others are by planting grasses. Others, there are geotextiles in it. So there's are a lot of measures that you can protect both the downstream side of your. So of course you have to protect the downstream too, so that this should be washed out as an effect to that of the pressure of seepage also. So because the other failure is of seepage. So here we go with that of the seepage failure. There are two types, which is actually there is only one event that happens for that of seepage, which what we call the piping. But there are two because the material of your dam is made of an earth fill or rock fill. So there will be seepage through the body of the dam. That's why piping there occurs through the foundation and piping through the body of the dam. So when there is a large pressure of seepage, there is a formation of cavity and movement of fines downstream. So that's why it is called piping, because it turns out to be a pipe all throughout. So take note that it is now hollow, although water is going through. But the problem is if because the pressure is not actually steady all throughout the time. So in terms of time element, it could be of high pressure. Sometimes it becomes lower. So take note what will happen if this hollow area, if there is no water anymore, or if the water is not that much. So this foundation and this structure will settle. So there could be, of course, problem in terms of its stability already. So another one is conduit leakage. So if there are conduits that are installed, then there are leakage. So it turns out actually that there will be water in it, and it is similar to that of the piping also. So sloughing downstream of the two. So of course, because of the pressure of this seepage, so there is a slump at the downstream phase. So this is also a failure. So water cannot drain out, causing high pressure in this area. So for structural failures, foundation slide in embankment. So it could be either from the construction method in terms of compaction or that of the material that was used. So sliding of upstream phase due to sudden drawdown. So there will always be like this, especially during the time that, of course, if the water here is the water impounded here is coming from, of course, from the mountains, from the nearby areas, which is just a runoff during heavy rains or in the event of rain. But during summer month, of course, there is less occurrence of the rain, so there is a drawdown in it. So especially if it is a rapid drawdown, so it can cause the sliding of the upstream phase because these areas already maintained its slope and its stability because of the pressure of the water. But when this water is now eliminated and goes to a lower level, so this could lead to that of the sliding. So of course, foundation settlement. So the embankment itself and the foundation could settle. So it could be a problem of the bearing capacity. So that's why it is part of the analysis also. So, but I mentioned earlier that we will not be looking into this analysis in terms of settlement, the stability of the foundation, in terms of the bearing capacity. So here are now the design criteria. We know already the features, we know already the causes of failures and some of the basics of the earth dam. So if you are now tasked to do the design of an earth dam, for example, you are working in an agency wherein you are required to design an earth dam for in a certain location just intended for a small area of or farmlands. So here are the design criteria. I just summarized here taken from the different literatures and codes in terms of how they do the design of an earth dam. So here are the basic requirements because we have to consider first everything from the materials itself and the proper analysis that we are going to do. A field of sufficiently low permeability. So we need that field with that of the material. So with low permeability. So once you get the source, then it will be tested in the laboratory and you are going to check in terms the permeability. Of course, it is the value of K that will be inputted in the seepage analysis. Barrow pit should be as close to the dam site. So it talks now about costing. So it is just about costing in that sense. Sufficient spillway and outlets capacity should be provided so as to avoid the possibility of overtapping during the design flood because it is one of the failures. of the design flood. Failures of the earth dam when it exceeds with that of your design flood. So we have to be careful in computing the maximum height of water in the upstream side. Then sufficient freeboard. So you have to decide what value of the freeboard that you're going to provide. So in this case, you are going to consider the wind setup, the wave action, the frost action if you are in the frost area, and of course earthquake motion. So another one that we are not going to will not be tackled in the analysis is the dynamic analysis. Of course the software, I hope I can, but I will show some features in the software because it is also powerful software that can simultaneously analyze also the dynamic analysis to analyze the part where in there that if the design dam is prone to liquefaction. So it is of another topic also. So the seepage line should remain within the downstream phase of the dam so that no sloughing of the phase occurs. That's why you are going to include some other measures like the one that I have shown in the figure, which is the drains or the filter drains. There is a little harm in seepage through a flood control dam if the stability of the foundation embankment is not impaired by piping, sloughing, etc. So we have to consider these things. But a conservation dam must be as watertight as possible. So there should be no possibility of free flow of water from the upstream to the downstream phase. So another thing to be considered is that the upstream phase should be properly protected against wave action. So we are going to include also slope protection. So it is not only on the upstream, of course, in the upstream because of that of the effect of the wave action, but also with that of the downstream, you are going to include also slope protection. The portion of the dam downstream of the impervious core should be properly drained by providing this one, the one mentioned earlier in the previous slide, the filter drains. Or sometimes it's called two drain, the chimney drain, etc. But those are all drains. The upstream and downstream slope should be designed as to be stable under worst condition of loading. So everything that is loaded in the earth dam should be accounted in their simulation. So you're going to input the if there are surcharge loads, the effect of the water pressure, and so on. Of course, the weight of the dam itself. So analyzing both the slope stability of the upstream and downstream is also very important. The upstream and downstream slope should be flat enough as to provide sufficient base width at the foundation level so as to provide suitable factor of safety. That is one of the hint. So, but of course, having it flatter and more flatter, it will end up having a bigger cross section and it is connected to that of a higher cost. That's why we have to locate which one is the most safest and at the same time lower in cost. So in manual calculation, you're going to repeat and calculate again in terms of the factor of safety. So in terms of slope stability, because in slope stability, what we are aiming here is the value of the slope stability factor of safety. But in the software, it is just very easy because it is just in one click or just a few minutes, you can have the different analysis by changing the slopes, changing the base width, changing the crest, changing the freeboard, and so on. So it is just very easy. So unlike the manual calculation, it will take time. The embankment slope must remain safe under critical condition. So here are from the US Bureau of Reclamation a table because you are now going to so we have learned the different design criteria. Those are guidelines and recommendation in terms how are you going to prepare now the preliminary design. So since you have it all, let us now create the preliminary design of the dam that you're going if you are tasked now to draw the cross section of the preliminary design. For the freeboard, you have here a table from the US Bureau of Reclamation. So it depends on the spillway type or the height of the dam. So you can have there the minimum freeboard over the maximum water level. So if it is of any height, then it is an uncontrolled spillway. You can use between 2 meters and 3 meters. So 2 meters actually is that of big enough to have it as a freeboard. But then to some other designers, they have it maximum 3 meters for safety factor. But take note that increasing the freeboard is actually incurring a higher cost. So other to use a critical sound design, they make use of the average of the 2 and 3. So they use the 2.5 meters. So, but then it is just a suggestion from the US Bureau of Reclamation. Later on, once you have drawn the preliminary design, you can still make changes if based on the result of your analysis. So for the height less than 60 meters, so you have 2.5. Height more than 60 meters, you have 3 meters above top gates. So this because of course these are of general dams because imagine an earth dam of 60 meters, so it is not actually not anywhere possible. So what we can use for if you are just going to design an earth dam, you just use this any height. So for the top width, what is suggested is using this formula. So the top width is designated as A. So the recommendation is h over 5 plus 3 for very low dams. So you can use this one for earth dams. H is the height of the dam. So of course you are going to you can analyze now the height of the dam because you have the design flood level or the maximum water level and you know already the freeboard. So the maximum flood height or the maximum water level plus the freeboard, that is the maximum height of or the height of the dam that you're going to design. So based on that, you can now determine the value of A. So for dams lower than 30 meters or dam higher than 30 meters, you have there the equation. But you can use this first equation because it is only for low dams. So we also have here a table from Tersaji in terms of slopes. But this time the slope suggested by Tersaji is based on the type of the material. So what type of the material you are going to use? So is it a homogeneous? But of course it is well graded. So of course you are going to consider that one if it is an homogeneous dam, it should be well graded. So the upstream should be, take note that the format of this table from Tersaji is height, not the height, horizontal, vertical format, no? Because in the Philippines we are used to that of the vertical horizontal format because from the definition of slope which is the rise over run. So when we are asked to define the slope, it is the vertical and horizontal. So like 1:2, 1:3, and so on. So the one there which is the vertical will always the first in the format. So in here it's the opposite. So I did not change it because I just scrapped it from the table of Tersaji. So if it is homogeneous, the upstream slope is 2.5 is to 1 or 1 is to 2.5. Then the downstream is 1 is to 2. So you can have it first. The preliminary design, you can use now this one. You have already the crest, you have the freeboard, you have the height of the dam. Then knowing now this upstream and downstream slope, you can compute the base width already. So for homogeneous, coarse, silt, you also have here the 3 is to 1, 2.5 is to 1. Then homogeneous, but the type of material is silty clay. If it is less than 15 meters or more than 15 meters, you also have the corresponding upstream and the downstream slope as shown in the table. If it is sand or sand and gravel with a central clay core, you have 1 is to 3, 1 is to 2.5. And sand or sand and gravel with reinforced concrete diaphragm, so you have the 2.5 is to 1, and in the downstream 2 is to 1. So based on this table, you can actually just have it first part of your preliminary design. It doesn't necessarily mean that it is your final design, because we are just having it as an estimate or an assumption for the preliminary design that we can make. So after which, then you can now proceed to the analysis in terms of the different types of analysis for earth dams. So here is another one from a table from a certain textbook. So there is a full table of its recommendation based on the height of the dam. So the first column is the height of the dam, then you have the maximum freeboard in meters, then suggested top width, then the upstream slope and the downstream slope. So for earth dam, maybe it could be in here up to 4.5 meters in height. So more than one story of a building. So one and almost one and a half. So the maximum freeboard can be 1.2 to 1.5, which is lower than that of the suggested freeboard by the U.S. Bureau of Reclamation. Then the top width, you don't need to compute. You just have it 1.85 immediately if it is less than. So it is almost 2 meters. Then the upstream slope is 2 is to 1. Then the downstream slope is 1.5 is to 1. So if it fails in your analysis using this one, then you can change again the slope. Maybe the slope has a problem. Then checking another analysis, then if it fails, it could be now the material. So there are a lot of things to be considered when your preliminary design fails. So you can use also this table. So another one is the seepage analysis. So of course you are going to analyze the seepage when it comes to earth dams, because it is prone to that failure. So seepage occurs through the body of all earthen dams and also through their pervious foundation. So that's a problem because the seepage occurs in two different areas, the body and the foundation. So you have there the phreatic line, as you can see, the topmost. Then of course this one, if you still remember during our college days, this is the flow net process of computing the seepage. But of course nowadays it is in the actual design, we seldom, or actually we don't even use this anymore. It is just a theory from a textbook that you can estimate. It can be used for estimating only, but of course since we have already different simulation softwares by finite element, the seepage is actually calculated by the softwares. So in the flow net, you draw the equipotential lines, you draw the flow lines, then you compute immediately the seepage. So here are some of the formula. So seepage discharge through the isotropic soils. So when we talk of the isotropic soils, the permeability for both the horizontal and the vertical direction is of the same. That's why you only have here one value of K. So the seepage Q can be calculated in this formula. So the total number of drops in the flow net, using the flow net in the previous slide, and the number of flow channels, NF. Then you have the H, or the height of water. Then you can compute. You have now the estimated value of Q. But then it is of graphical method, so the level of accuracy is not that much acceptable in the present calculation that we have as computer softwares. So, but for non-isotropic soils, you have this formula that you can use also in the flow nets. So non-isotropic, so you have the K horizontal and the K vertical. So of course the K value there, the permeability will be taken. If you are structural, oh no, the dam designer, you just get the value of K from the laboratory of your company. So they are the one to do the who prepares the test of the soil that will be, or the earth material that will be used for the construction of earth dam. So if you remember there, the drawing of the phreatic line or the topmost seepage line is to draw a parabola from a certain point to the two, or to the point wherein the seepage will go out. So from the equation of the parabola, so this is just a summary because of course it is a lengthy discussion of how what has been done with this formula. So the square root of x squared plus y squared, which is from the parabola equation, is equal to that of the x plus this distance, the focus to the directrix. So from that figure, you are going to determine this distance, the focus from the directrix. If you are going to designate FD to S, which is the distance from F to D, so you can have now this formula. So with that of the equation, because you have the parabola, so at different points you have the x and y points, you can actually determine the value of S. So with that, you know the value of S, you can actually substitute it in the seepage discharge. This one is more exact in as compared to that of the flow net, because you multiply this distance, this S value, to that of the permeability, then you have now the value of the seepage discharge. So in but then again, it is this one is graphical. I in my subjects, which is on the hydraulic structures, when I am teaching in Oman and in Ethiopia, because I am handling hydraulic structure 1 and 2, which is the design of hydraulic structures, and hydraulic structure 2 is the design of dams. So there is a specific course for that. So the whole of the term is just intended for the whole design of dam. So this is graphical. So of course in the classroom you are going to teach them the theoretical part, the previous method, which is actually graphical in nature. So they are going to draw the parabola, so manually. So and it's very easy if they know already how to plot it in the AutoCAD, because it can be drawn exactly and you can pick different points of the x and y for you to identify the value of S. Then if you have the permeability, you have already the value of Q. So that's how easy it is, but it's very difficult manual drawing of the parabola or the phreatic line. So if you can see, this is the phreatic line. So this is the topmost seepage. But drawing that, it is not actually starting at point B, which is the intersection of the water level and the upstream slope. So it is somewhere at point A, which is an imaginary point, and how you are going to draw that point A. So from point G, which is the hill, you just draw or project it going up to the water level, then mark it as H. So you have now the distance HB. So you can measure HB. So from that HB, you multiply it by zero point 0.3. That is the estimated distance of point A to that of B. So if you can have that, you can now draw the parabola. So drawing now this parabola going here, if you have this filter. If you don't have this filter, it's just very easy because it is somewhere here also. But it is of different method if the seepage will go out on these two. So still remember in the previous slide, the seepage is within the seepage can go out within this area, which is a maximum of h over 3. So if you have the drain, so it will go here. And this becomes the center of your parabola. So of course there are by geometry you have to determine the focus and the directrix. And you can have now there the F and the D. So that is the distance which is equivalent to S. And that is the most important value there, the FD. And you just multiply it with that of your permeability. And that's it. You have the value of your Q. So, but again, although there is a formula given, there is an empirical formula, but then the process of finding the FD is still graphical. So there they go. If you don't have the drain, so the seepage could be somewhere here. So there are some of the assumptions in terms of where is the parabola and how we are going to draw the parabola. So this is actually the equation for your the values here of A, then the this delta A also, and so many other factors. It's just very easy if you have all the guides. Of course, ha- teaching this to my students, you have to come up with a detailed calculation of drawing the seepage line. But then the purpose of why I am actually discussing this or presenting this is just for you to have a brief overview of the theoretical part of seepage. Because if you have later the software, actually you don't worry about these things because the software will give you or plot exactly the location of the phreatic line. And of course, it will give you easily what you are going to get there is actually the value of the Q or the discharge and the exit gradient. So here's an example of the phreatic line with the dam section is homogeneous and without filter. So that those are the assumptions. So for the zone embankment, it's very difficult in terms of the manual or the graphical method because you have now the different materials in it. So I think that's it for this part in terms of analyzing what are embankment dams. So I hope you had learned a lot on the differences of the types of embankment dams, the earth fill and the rock fill, and some of its failures. And I also hope you had grasped the design criteria and the guide in terms of coming up with the preliminary design of the embankment dam or the earth dam that you are going to have it as your, for example, if it is part of your job that you're going, part of your task that you're going to design a dam. So you can use the guides as mentioned in the US Bureau of Reclamation or by Tersagia. There are a lot of books that you can actually use for understanding the preliminary design. There are a lot of books in the hydraulic structures. So one book that I use is actually the hydraulic structure by Novak, and it is a more detailed discussion of mostly for the earth dams because it is inclined mostly in the geotechnical and the water resources side. So you are going to have a preview of the hydraulics part because of the water effect, and at the same time the behavior of the soil because it is made of earth and the foundation itself is of course is an earth material. So with that alone you have to go back to the basics of geotechnical and water resources. That's how dam engineering is all about. Except, of course, if it is made of concrete, because you have to inject there some part of the structural analysis because it needs reinforcement and so on. But I hope the purpose of discussing only this embankment dam is just for to give you a brief overview of the preliminary in terms of how you are going to do the design process. So I am expecting that you can now have or you can now draw your cross section, the preliminary cross section, because after which you're going to proceed with the proper design of the embankment dam, and it will, because we are going to use simulations by finite elements, so we will be using softwares. So the most important thing there is for you to understand the theory first before we go through with the software, so that it's very easy to comprehend everything inside the software. So I think that's it for this topic. So we'll just proceed to. Okay, so let's move on to the next topic. This time I'll show you some of the pictures from the different failures in terms of slope, and it is caused by, most of them is actually during the flooding and during typhoon events. So of course, the Philippines is always prone to typhoons, especially in this area. Actually, I am from Samar, so along this, the Samar Leyte area, which is facing the Pacific Ocean, is always prone to different typhoons all throughout the year, and it is always the main cause of landslides, failures of the different slope. Of course, not only with that of those structures, but of course to the livelihood of those people. And going from Samar Leyte, it will move on to the Bicol area. So that is the problem, and we have to make sure that all the hydraulic structures, or those structures that needs analysis in terms of stability, should resist all those forces and cases wherein it will become fully saturated. So that is the problem. Of course, not only in this area, but it's all throughout the Philippines, and in other areas like in the north, going to Baguio. So there are some problems along the highway. There are always landslide. So when we talk here, although our topic is about earth dams, but because it is about slope stability, and we are looking into an analysis of how we can come up with the analysis that it will not fail during those events. It is also actually can be compared to those analysis in terms of slope of those embankments. So, or any sloping, natural slope areas, such as along the highways, the river banks. So it can be applied also, the same principle. And the software that I will be showing to you later are actually not only limited to that of the design of an earth dam. Of course, all of you attending this webinar are not working on those agencies that designs dams, or in charge of the construction, the design, and the monitoring of hydraulic structures. But the general principle in terms of slope stability, and later on we will touch also some part of seepage, so it can also be applied to other kind of structures, or even those in the construction site wherein you're going to do excavation. So it can be also applied, because you're going to cut the the excavation area by slope. You can have it vertical. Of course, in terms of the economic or the cost impact, the managers may request for a vertical cut, but it depends on the type of the material. So the same principle that we're going to use in here. So you will be amazed later how powerful the software is, and how you can apply it in your own field. So this is a picture which is a flood damage. So if you can see, it is in Bulan, Sorsogon. So flood water swept away a section of road, which is always the the incident in those areas. Even in my area, in Samar, in Samar Leyte area, especially in northern Samar, during typhoons, especially if this is very heavy and it takes days for the rain event. Once the whole area will be flooded, or is flooded, so most of the roads will be damaged. It will be swept away. Some of the embankments, the road embankments, those the river controls, so the different drainage canals, all of which will be damaged. So it is just a cycle that every year after a typhoon, some structures will be damaged, and the following month it will be repaired again, constructed again, another budget, and it will always be the same cycle. And we cannot deny the fact that those municipalities, especially in my area, are not that rich municipalities. The IRA, of course, they are having a very low income in terms of in terms of revenue, and they cannot provide those sophisticated or high-tech structures. So what they did is just for an immediate solution that they have to concrete the embankment without even soil exploration, because soil exploration is very expensive also. So those are the things that are the actual scenario happening in areas. Even if you are going to construct small earth dams for your maybe not for the whole area of the farm, but for your own farm only, if you have hectares of lands and you want to impound water and so on. So analyzing that one is very expensive in terms of the preliminary investigation. And here in Metro Manila, it's very expensive, and they cannot go away with it because it is actually mandated in the NSCP and the local codes and the building codes. And they are fully implementing that one. But we cannot deny the fact that in the provinces it is not the real scenario. Even in the construction of residential houses, they are actually just approving without even presenting the calculation report, the soil investigation. It is all just an assumption. Sometimes they just get it from textbook or from the internet, the soil bearing capacity and everything. So that's the problem, and that is the reality. That's why it happens in a cycle, that every typhoon, even not a typhoon, in my place, even it is not a typhoon, it is just a rainfall event that will last for a 24-hour rain. How much more if it goes through with a 2 day or 3 days rainfall event? So it would damage different structures, not only the farm areas, the agricultural aspect, but most of the structures in the area will always be damaged. This is a landslide in Mainonong, Sugod, Gaho, and Bariis in Albay. So this is an area in Albay. So if you can see that the type of soil, the type of material is very loose due to the saturation, the level of saturation. So during rainfall event, so of course the whole area will be fully saturated, and it of course will have runoff, and it causes the soil to be loose and will be prone to this kind of a failure, which is landslide. And this incident is actually true not only in the Albay area, but all throughout the whole Bicol area, because the area is mountainous up to the Quezon province. So same as true is in Baguio, because along the highway those are mountains. So the same principle, if you are going to analyze the slope stability for earth dams, it is the same method that the analysis can be applied in this kind of the natural slope. But the problem is, one thing in the software, it is just very easy to simulate, it is just very easy to model. You just, if you have the survey of the topography and you can model the slope, it is just very easy. The input parameters are very easy to input inside the program. But the problem is, where are you going to get all of those data that you're going to input? In the more column analysis that we're going to use in the slope stability analysis, it's just very easy because there are only three parameters needed in the analysis, which is the unit weight, the cohesion, and the angle of internal friction. Of course, the angle of internal friction can be found in the different literature and is connected to that of the cohesion and unit weight, or the type of soil. So, but then even the unit weight, the LGUs doesn't have laboratory results for their soils. And take note, those universities in Albay, in even in Sorsogon, in my area, in Northern Samar, in Leyte, there are a lot of big universities there, right? So if you are looking into those universities, they are offering civil engineering, and definitely all those universities have their laboratories, and those laboratories are actually equipped with those of the required apparatus to test even just the unit weight of the soil. So if that can be utilized by the LGUs of the different areas, some of the research of those colleges or of those universities, actually you can actually come up with a good model, come up with a very good analysis, not only just by assuming parameters. In Metro Manila, if you are going to look into the soil map, if you are going to get from even from the NAMRIA, the different maps that they have, all throughout Metro Manila, they already have the different parameters and the soil types all throughout the metropolis. But then, if there are cases that some structures will be constructed, if it is a high-rise building, they are going to do the soil exploration again. So to come up with exact or the current, or not that much with the current because it will not change every month or so on. But then the the properties of soil underneath are different from different points. The availability of boreholes, if there are in the area, depends on the spaces, right? So you cannot have it spaced in a very short distances because it's very expensive every borehole, and it depends on the depth of the exploration. So that's one of the problem that those LGUs from the provinces encounters. So how, although if it is a big structure such as big dams for multi-purpose dams, of course soil exploration will be included in the budget, so it is not that much of the problem. But if it is in this case wherein we're looking into the proximity or the occurrence of these failures, the problem of those LGUs in the provinces are the budget for the soil exploration to determine if the area is that needs improvement. And another one is if it is analyzed, for example, if we have now the software, okay, we had analyzed, we have all the data needed to simulate, then how much is the cost? Of course, we will not be only protecting this area that is this area that's already failed, but all throughout the whole area we're in, it could be analyzed to be prone to landslide later. So that's are the actual problems that they may encounter. So there's also another one. So spillway in Tiwi Albay. So if you can see, it fails this part of the structure. So it could be the pressure underneath, and of course the foundation of which is fully saturated because of the water flowing in it during the flood event. So it could be one of the problem. Of course, we cannot just say because due to that picture the exact problem, because you have also to analyze what is the failure. It could be the structural failure. It could be that those that I mentioned in the previous slides in terms of what are the failures that for earth dam that may occur. So there are different types of failures, as seepage, the hydraulic failures, and so on. So this one is in Baguio, the one I mentioned. So not only in the Bicol area, in Samar Leyte area, but also it is true in the areas going to Baguio. So soil erosion, landslides, and so on. So there are, of course, protection. There are this structure. So, but then how are you going to analyze also if it can resist of or if it is safe? So actually the software can do all of these things, but then the one that I will be showing to you is just an educational license software. So there are limitations. But if your company, the same with my company before in abroad, that we have the professional license, so you can actually model the different materials, including concrete and reinforcement, and some other, even the grasses, because it is part of the soil protection, the slope protection, which is planting grasses using the different textile, the geotextile, all throughout the area or the slope area. So can be modeled also in the software. So this is in Camarines Sur landslide. So that is always the problem. Actually, if it is along the road and it will damage actually the structure, and sometimes it cuts the national highway. So this is also a picture of a landslide. So there is a mass that fails. So it could be in its history or the previous event. In this one, there are already cracks, and the whole area is actually prone to or already is very weak. So that's why it fails. Then this is in Lower San Fernando Dam. So the problem in there is about the liquefaction. The software actually analyzes the also can be utilized by analyzing the dynamic analysis of hydraulic structures. For example, earth dams, you are going to subject it to earthquake. So it is a dynamic analysis. And one of its output is to check which area would be prone to liquefaction. So it could be one of the problem also. So this one. So if you can see, this area failed. So this is also a failure of a tailings storage facility. So it is just small, but then there could be some problems not only of the slope, because if you can see, it is just a very small storage facility. So but then there are could be some problems in terms of seepage, the piping effect, and other causes of failures. This is in Peru, if you can see. So this the whole mass actually failed already. So it become loose and it fails by landslide. This is in Cusco, Peru in March 2018. So the problem in this area is how you are going to monitor. That's the main problem. If or because sometimes seeing it in that area, which is very, it has a very nice view, you cannot just detect if it when it will fail. So the problem in there is there should be monitoring, but how what agency should be monitoring all those natural slope all throughout the area? And this is similar to that of the Leyte event before. So this slide, this mass slides down to a certain community below that killed hundreds or even thousands of people. So this is one also problem of a downstream slope, although it is in 1948, but it is not that clear. But this is a downstream slope failure. If you can see this one, so there are already cracks along this area. So this is in Benguet province during the typhoon Ompong. So the same scenario. So those in the mountainous area, of course, we most people they look at it of just a simple failure because due to typhoon and rainfall events. Of course, because the main reason is that the whole area will be fully saturated. So the problem that the type of soil, if it is saturated, it will become loose. So and of course, we cannot deny the fact also that it is one of the effects of the deforestation. No? So we have to take care of those area, and some areas doesn't have any more trees because of illegal logging and so on. So there are a lot of this kind of problem cannot be solved in just a one click by those of the experts. Maybe sometimes even me, I am thinking before where are the experts? We are telling ourselves that Filipino engineers are very good engineers and excellent engineers. Why are there so many Filipino engineers working abroad, known to be as best civil engineers and so on? There are a lot of doctors, there are a lot of masters in water resources, in environmental engineering, graduates from the different known universities in Metro Manila or in the Philippines, but how they are going to contribute in terms of solving those problems. So this is a lot of there it needs a lot of a planning because the problem is it is the problem is surrounded by different aspects, not only with that of because as civil engineers we look sometimes into the structural aspect only, if the structure can resist, and sometimes there are a lot of things to look into consideration in terms of the structural integrity. But looking at problems like this, there are already societal concerns, environmental concerns, political concerns, the health and safety, and there are a lot of things to be considered. It happened during my master's program. We visited a certain area in Pantabangan Dam before it operates that time. So I think we are the last group to visit the area before the water or the gate will be opened for their testing. And during the interview, because we're gathering data for our mini thesis in terms of how dams are being constructed and what are the problems. So we thought that time that looking into as a civil engineers in charge in such project, because it is a multi-purpose. The purpose of Pantabangan Dam is to generate electricity, to water the different farm areas, and to supply water towards the Manila area. So it is a multi-purpose project, and there are some fishery development projects intended for the people there. But looking into some of the details, I become interested not only with that of the structure, but before the conceptualization of the project, and it took years to that the project will be implemented and will be approved because of some social issues, and those areas that will be the area in which the project will be constructed are the places of the different indigenous people such as the Bongalots, and they have to convince those people to that they will be displaced and they will be given a specific area, and of course the people will be resisting, and those are it took years for them, for the government, for the negotiation process, and so on. And take note, you are going to the design of the reservoir will take a lot of hectareage that will be flooded, so the whole ecosystem will be what this will be damaged because you are restructuring the whole area into a multi-purpose project, which is that Pantabangan Dam. So it is not only the role of a civil engineer to be part of the analysis of the structural integrity. Of course, that is our main role in the project. But we have also to consider the fact that in the team in the planning team, there are a lot of agencies, there are a lot of organization, there are a lot of concerns that we have to consider. That's why, if you can see nowadays, if such projects are being implemented or being conceptualized, there is what we call the environmental impact assessment. So we have to consider everything. But of course, because of I know the fact, we all know the fact that in in the process there could be some problems, there could be under the table activities, and so on. So the concept of the environmental impact assessment is very nice. It's really looking into the impact of the different activities, not only to the human being but to the environment and to the whole ecosystem. I had been part always in the development of the environmental impact assessment of all of our projects abroad, and it is very nice to see people giving their ideas, what will happen to the habitat, especially to the marine habitat, because most of our project is in the sea area, such as the shipyard, the dry dock, the power plant, those power plants. So everything, especially when we were working a project in Sultanate of Oman, where in the whole area, it is a virgin area along the coast of the Sultanate of Oman, that they are going to build the two dry docks. And the area is, if there are we hired a lot of divers to look into the condition of the area, and there is a lot of corals in there. And what after the analysis, after submitting the environmental impact assessment, the proposal is to transfer all the corals, and take note, it is part of the budget, and the company will be going to hire professional divers just for the transportation of those corals to another designated area. So there's a lot to be considered. It is not just simple as sometimes we blame the government, sometimes we blame those people sitting in the government, why it happens, the landslides happening, and so on. Because there are a lot of things to be considered. So it is not just simple as it is. But of course, if some precautionary measures has been done in place, or has been discussed in place to avoid such event, it would be better. Of course, better if there is no loss of lives, loss of properties, and so on. Okay, so of course it is always part of the issues and concerns as regards to hydraulic structures. Not only in the hydraulic structures, but in other structures that we build. So for high-rise buildings, like those things, the problem is only, I think, the area problem, the maybe the alignment, no, neighboring points, if there are complaints, and so on. Once you construct, there's no problem in it, because you will look into consideration the whole structure. So there will the it can only affect less compared to that of those of the hydraulic structures, such as dams, no, even bridges, and so on. So this is another landslide event in Bohol. Okay, so same failure. If you can say it is of hard material, but then maybe there could be some cracks in it, and that's why it fails. So this is in Davao City. I think this was already, because the picture during this time is already, they are already rehabilitating the whole area. And I think, because I've been in Davao and I presented this one, then they said it is now okay, the whole area. So it seems that slope protection has been done in this area. So this is in San Mateo, Rizal. Actually, this is always true in my province. No? So the whole, or part of the road, not only those of the municipal road, but even the national highways. So always have these problems. So the Baguio landslide, it is a yearly event in Baguio. We can always, during rainy season, we will always hear it from the news that there are problems in terms of landslide. This is also in 2018 Cebu landslide, but this is a mining induced landslide. So this is the one similar to that of in Peru, the Saint Bernard event. So this area is actually a community, which is the Saint Bernard, and the landslide, and I if I am correct, when I if I remember it right, it happens in the evening or early morning. So it all people are actually sleeping that night. But then during that event, some of the people that has seen or witnessed the event, that the people were advised to go to the, because that is a typhoon event. So they are advised to go to the nearest structure that would keep them safe during the typhoon, and it is actually the church. But then the church is actually located at the foot of the mountain, and they don't even know that this part will fail at that time. So there are a lot of casualties in this area. So this is in Negros earthquake, which is actually also similar to that of the events in the Dagupan area. So sometimes in those area there are a lot of liquefaction when there are events like this, like the earthquake. So because of course the shaking event, the pressure, so the effect of the water below will tend to rise its pressure. So those are some of the pictures that I had collected. So I think that's um, based on those pictures. I hope that you have engulfed into your minds the importance of slope stability analysis. So how are we going to prepare that analysis? During our college days, we know that some of the methods are all theoretical, right? So and it is based on the different theory found in the geotechnical engineering books. So, which are actually that is the basis of what we are going to do. But those are limited to that of how we are going to utilize those things because of a lot of parameters. And if you can still remember the different mathematical equations and methods, if you are going to apply a lot and more input parameters, so higher level of mathematics like integration, differential equations, Laplace theorems should be applied. So it has a higher level of analysis. One good thing is that the artificial intelligence, the use of neural networks, the use of simulations, softwares, and so on came at this stage or at this era of computerization. So that's why we have just to learn the basics. So what I'm going to do first is actually to discuss the basics. So just to review, this is just a review. We will not be doing some of the calculation because the software is just very easy and user friendly. And what is important there is for us to understand how the software do the arithmetic, do the calculation, so that once it gives us the result, it will only give us a certain value of the factor of safety. But the problem is how are we going to analyze? That is actually the role of the civil engineers. Other people may think that the role of the civil engineer is not anymore that much of the level of employability in terms of simulation and so on. They said that it could be done by other professionals, even clerks, actually even high schools. I presented this one to K-12 graduating class, and they are very interested, and actually they can do it by their own. But the problem is how you're going to analyze if the figures in the output view will tell us the other way around, that we are expecting or it is a failure value. It is only the civil engineer that can analyze it and can give solution. So that's how our profession is very important in terms of this. It doesn't mean that we are already in the advanced era, or we are already in the time of computerization, time of artificial intelligence, that if we don't know that much of the algorithms, we cannot actually compete with other professionals. But of course, programmers prepare the other professions, like the computer experts prepare the software, but then it is only with the guidance of the civil engineers. And that's how we will enter in that part that we are going to do the analysis and giving the mitigating measures or solutions to that of the problem. So in this time, we are going to analyze the slope stability. So let's try to dig into some of the problem. This is just some of the basic. I did not select some of the analysis methods that are not that much important in the software because the software utilizes the more column analysis. So with that, they are using the slip surface method using the Swedish slip circle method. So, or the Swedish slices method. There are, at present now, if you're going to look into some of the textbooks, there are a lot of terminologies that is termed to that of the original method, which is the Swedish ordinary method of slices. So it is the method of slices that we are going to discuss this time. So this is a simple earth dam. So if you can see, it is not that of the simple because take note the crest they are using it as a roadway. So the water is impounded on this side on the upstream, and although I don't know yet with this picture if what is the purpose of impounding water. So we just have it as it is. So of course you have the surcharge load, which is the load of the vehicles on this one. So you have to consider the maximum water level on the upstream side for you to compute the hydraulic pressure on this part. And then you can analyze. Of course, the most prone area for failure of the slope is the downstream because the pressure here is pushing to the right towards the downstream. So we will always look into consideration first is the downstream. But in the software, you can do the both sides of the slope, the upstream and the downstream slope stability analysis. So here are the three considerations that govern the design of an earth embankment. Although it has been mentioned already in the previous slide in the preliminary design, if you remember, there are preliminary values if you are going to consider the crest, the slope, the height, and so on. So the first thing to be considered is the side slopes must be stable. That's why we have to turn that the term is slope stability analysis because you have to make sure that the side slopes are all stable. And how we can do it, as according to some of the authors, the the flatter the slope, the more stable it is. But you have to look also into consideration the cost impact, the economic part of that project. If you're going to have it flatter, the cross section becomes bigger. And knowing that the cross section becomes bigger or larger in terms of area, it talks about the cost of the structure. And of course, you are going to multiply it because what you are going to do. If you still remember, when we do the analysis of them, it is always a 2D analysis, and it is analyzed per 1 meter length. So you are going to consider the total length of the structure. So we have to analyze that it is safe and it is stable both in its structural integrity and of course in terms of the cost. So we are going to look into the most safest slope that both can actually address our concern in terms of integrity and stability and of course the cost. So dimension must be sufficient to control seepage. So another one is there are other theory of seepage that tells that you can actually reduce the pressure if you are going to prolong the travel of the seepage. So having it, if it is, we are talking here now of the seepage through the body of the dam because we are looking into the analysis of the side slopes. So if you're going to prolong, so better to have it flatter so that the width of the cross section is more bigger, or that so that the creep length or the travel of seepage will be longer so that when it goes throughout the point of exit, the pressure is not that much high. And if you're going to compute the exit gradient, which is one of the most important parameter in analyzing the stability of earth dams, is already small. So base width must be long enough. So how you are going to do it? So flatter again. So that's why the three considerations in here is actually looking into the cross section. So why you are going to have it long, or that the width is that big, so that the width of the dam can be distributed evenly all throughout the area. So number one is, of course, you're not going to overstress the foundation, although we are not doing the analysis of the foundation, but you have to take note also that the structure is laid on the soil foundation. And what are in the geotechnical aspect, we are going to analyze the bearing capacity, the stress, the strain of your foundation, if really it can carry. Aside from that, if the seepage, if there are uplift pressure, and so on, there are a lot of things to be analyzed. That's why in this webinar, in this 8 to 9 hour webinar, we are just limited to that of the stability analysis in terms of slope, and a little bit of the seepage. But then in the simulation later, because we will focus more on the simulation, we have you can have a full view of how the slope stability analysis and the seepage analysis is being done in the software. So an earthen embankment usually fails because of the sliding of a large soil mass, and that is true with that of the soil properties or the type of the material that you're going to use. So, and since it is an earth material, so it is always prone to sliding effect. And it is caused by the different scenarios, different effects. It could be the pressure, the seepage, or with that of sometimes the problem is in the construction method, the problem of compaction, and so on. So there will be a soil mass that is along a curved surface. So that is part of the theory, which is based on the method of slices. So you are going to draw that curved surface that is considered to be of the sliding large mass. And based on that sliding soil mass, we are going to check if the factor of safety is within the tolerable limit for stability analysis. So this is the Swedish slip circle method, or the most common term for this is the slices method, or the method of slices. It is known to be Swedish because, of course, the author are Swedish, so they call it as a circle. So it is just similar to that of the integration, wherein if you have what's this an irregular figure, and if you're going to do by integration, so if you're finding the area, so you are going to run an integrated area, a very small area, which can be considered a rectangle. Because knowing the rectangle, we assume that the the width and the length is known based on a certain equation, and if you're going to run through a certain point, starting point to that of the end point by integration, you know already the total area. So similar with this. So with that of the curved surface, this is now the curved surface that is mentioned in the previous slide. And you are going to divide the mass into number of segments. And those segments are known to be slices. In integration, it is the integral parts. So those are very small part. The problem is this method is graphical. The some of the exponents and some of the authors of this method says that the more number of slices that you are going to use in the analysis, the more the level of exactness of the value of the factor of safety that will be soon derived or calculated will be nearing to that of the exact analysis. But then if you're going to do it manually during the our college days, it's very hard. Why? Because you're going to compute the area of the slice, and this is a curve. So therefore, it is not what's this? It is not a square. It is not a rectangle. So you're going to do the calculation of the curve. So one good thing is that we have the AutoCAD. You can draw it in the AutoCAD, and you can divide it in the different slices. If I if I am the professor and if I give this exam to my students, I have to give the different areas a tabulated table for the different areas of the different slices. If, for example, I have to divide it into five equal width of the slice, then I have to give them the exact value of the areas of those slides because that is very important. Why? Because it talks here of the you are looking into the weight. If you remember when we take our hydraulics subjects in the college, we just analyze them in terms of the overturning and the resisting moment, and dividing it, we compute the factor of safety, and that's it. Here it is different because it talks about both of the water resources aspect and the geotechnical aspect, which includes the behavior of the soil. That's why the method of slices came in. So what you are going to do here is to calculate the unit weight. And this time, this is not the whole of the structure, only of this critical slip surface. Before, if you remember, you compute the total weight of the structure, take the moment at the 2, which is at point B, the overturning and the resisting moment, and divide it, then you have the factor of safety. Okay, so that's how simple it is when during our college days. But of course, in the geotechnical part, it is not just as simple as it is. So we are taking we are computing the factor of safety in terms of the behavior of the soil in this critical slip surface. The location of the center of the possible failure arc is assumed. So this point O. So it is an assumption. So of course you have to follow different assumptions of the different exponents or authors of the method of slices. In the method of slices, there are a lot of authors already. Even the software, they include I think three or four authors in it. So what I did is because they have a lot of not that much of big differences, but they are different in terms of the interpretation of how the neighboring slices affect its neighbor. So, for example, slice number 4, the behavior of that soil will affect slice number 5, number 3, and so on. So, they have different interpretations. So, what I did is to tabulate the different factor of safety of the different authors of their different interpretations. So the of course the factor of safety based on the different authors will have different values. Some will be the same, some will be different, but based on my experience, it is just very insignificant. It's just very small. So the Earth mass is divided into number of vertical segments. This one we call that one slices, and the center. O is the center and R is the radius of the possible failure. According to some of the authors, if the angle of internal fraction is lower than 15 or very low, the curve or this curved surface should touch the 2. So that is the ideal. So okay, that's why, because this is a graphical method, when you have it in the classroom or as an assignment, the assumption is the curve should always touch the 2, so that when you assume the center, this point O, it is very easy to run the circle. So if you have the protractor or any device that you can draw the a circle, so all the if you draw the circle, then all of those that will the arc that will touch the dam will be now the critical slip surface, right? So if you can see there, if you have one, I think there are 6 slices in here. You can compute the weight of the first slice, weight of the second slice, and so on. So you need a unit weight of the property of the soil. And the problem now is the area. Okay, so here are the forces acting on the different slice. So you are going to take one slice and analyze each slice. So every slice you're going to compute a factor of safety. So one good thing in the software, it can analyze thousands of slices in just a minute or in just a few seconds and so on. It depends on how the complexity of the cross section or of the problem. So the self weight W, which is the weight of the slice acting vertically downward through the center of the gravity. So you are computing here not the whole of the dam, but the weight of the slice.
Then the cohesive forces acting tangentially opposite to the direction of probable slippage. So the cohesive forces are actually those forces that is an effect to that of the neighboring slice because you have the value of the cohesion. That's why we have to select a material that is cohesive. But that doesn't necessarily mean that clay is a cohesive type of soil that you're going to place plain clay with that of your structure because there are other factors not only with that of the cohesion. So what you're going to do is by analyzing the cohesion, if you have the value of the cohesion, you can compute now the tangent force acting opposite to the direction of the probable slip surface. There will be, I think, some of the presentations later. So because you're going to, if you're going to do the calculation manually, so there should be the normal and tangential forces. That is an effect to that of the neighbor because your neighbor has a cohesive effect to that slice. For example, you're going to analyze slice number 3, there will be a tangential force as an effect to slice number 4 and number 5. So both sides of slice number 3, there will be two forces. That is tangent. So another force is the normal forces. The soil reaction across the arc. So if you can see, you have the arc there. So there is also a force of the mass outside of the slip surface, and that is the soil reaction because you are going to extract that one. It is similar to that of in the mechanics. You're going to draw the free body diagram. So if you take one slice, then you draw the different forces acting on that slice. So the weight of that slice, the cohesion of the both sides, and the force reaction due to the soil reaction from the arc. So it is below. So and that problem is can be solved using the angle of internal friction. So from the three forces that I already discussed, it is very clear that you need the unit weight, you need the cohesion, and you need the angle of internal friction. Okay. The soil reaction on the vertical sides of the slice exercised by the adjacent sides slices on the right and left respectively. So those are the effect of those cohesion. Then of course the pore pressures at the base of the arc and left and right side of the slice. So meaning it is also very important to determine those pressures, especially if the seepage analysis has been already done and you can draw now the seepage line, and that seepage line will determine which part of the critical slip surface is saturated or not. So from that diagram in the previous slide, wherein you draw there the slip surface, the curved surface. So you are going to draw there the seepage or the phreatic line, which is the highest line of seepage. And you are going to determine now which part is already saturated. Because of course, if it is saturated, the unit weight that you are going to use is the saturated unit weight. And on the top of that, above the phreatic line, will be the dry unit weight. So this is yes, this is the diagram. If you can see, you have the different slices, 1, 2, 3, 4, 5. Then this one, the last is the sixth one. So you have the weight there. So in this curve, you have the curve, the effect of the soil reaction in here. So there is a diagram here on in terms of the normal. So this is the normal, and you have the tangential force on that part. So this is a sample of the method of slices. So if this is the structure, for example, this is your embankment or the earth dam. So you have assumed center of the circle, and you have this slice, different slice. So what you are going to do is to take this slice. So extract this slice, and these are the forces acting on that slice. So of course, you have the width B. Others, they use the same width B. They just divide the length of this area, which is inside of the entry and the exit of the slip surface, so that later, if because I will show later some of the prescribed table or the tabulation format in terms of this calculation when you are doing it manually. But of course, I'm not encouraging you to use the manual method because most probably it will become the result is more prone to errors because of the calculation of the area and so on. Only if you are going to use other sophisticated software like the AutoCAD to compute the areas, specific areas. So you have the weight, which is downward. So this is the the forces, like a free body diagram of this slice. So if you can see, you have the normal and the tangential forces, this one on both sides, which is an effect of the cohesive forces of the neighboring slice of this slice on the left and the slice on the right. Then of course this one is a curved area which has an angle. So this one, it is this area, this sloping curve. So you have also there the tangential and the normal force as a result of that of the soil reaction. The software will present to you all of these of the different slice. So it will present to you the value of the weight, the normal and the tangential forces acting on the different sides. So the problem is, as mentioned earlier, that the center of the circle is just assumed. So how are you going to assume that point? So there is a guide according to the theory of the method of slices. The location of the center of the possible failure arc is assumed. The earth mass is divided into the number of vertical slices. So first is, let O be the center. So of course you can use any other letters. So, but in this example, let us use that one. So I prepare one example just for you to understand how it is being analyzed. So O be the center and R is the radius of the possible slip surface as shown. Take note that it is a possible slip surface. It doesn't mean that it will fail. So what we are going to do here in the method of slices is to identify that slip surface and compute if it will fail or not. So let the total arc AB, so the whole arc, be divided into slices of equal width. So let us consider B as our designation for the width. So it is in meters. So it should be divided equally. So the slices will be numbered by 1, 2, 3, 4, 5, and so on. And let the weight of the slices be W1, W2, W3, W4, and so on. Okay, so it's just very simple as you can see. Of course, knowing it from even in the mechanics, computing the normal and tangential forces. So we have here some of the components. So taking into consideration the normal force, it is equal to the weight times the cosine alpha. And the tangential force is weight sine of alpha. So where alpha is the angle which the slope makes with the horizontal. So that is the curve surface. So that is the arc that we draw. So of course you are going to measure that angle. That's why I am asking some of my students in the classroom. They do it manually, but if it is an assignment, if it is a take home activity, I advise them to use softwares like AutoCAD to get the exact values of the areas for the weight and for these angles. So the total disturbing moment, which is the MD, so that's how they term the overturning moment, the disturbing moment. Because I use the uh, um, a British book because this is the subject I handle when I teach in the Middle East and in Africa, in Ethiopia. So most of their books are from they patterned from the British styles. So the terms that they use are of different. If you can still remember the format of their slope is not the rise over run, the vertical over horizontal, but horizontal over versus the vertical. So that's how they, because of course in the Philippines we pattern it from the American formats. So here, the disturbing moment is actually the sum of all the tangential forces. So times the r. So because it is a moment, and the moment is actually that of the radius distance, the moment arm. So since r is a fixed value, we can have this r times the summation of all the t. So the summation of all the t is the tangents of the different slices, so t1, t2, t3, and so on. So it's very easy to compute the MD. For the resisting moment, which is the same with that of our term that we use, the terminology that we use, it is actually the resisting moment. So it is the resisting moment over the entire arc AB. So the formula is R, which is a fix, times the summation of the cohesion times delta L, plus the summation of the normal forces times the tangent of the phi. So in here, you have the cohesion and the angle of internal friction. Of course, the unit weight is used for computing the tangential forces and the normal forces. So simplifying further, R is equal to MR is equal to R times the quantity, the cohesion, because cohesion is already a fixed number, a fixed value because it is taken from the laboratory, the cohesion of the material, times the summation of your delta L. And actually, it is the arc AB, this delta L, because that is the distance of the arc per slices. And the sum of all those is actually equal to the total arc, which is AB. So you can have it as C times the arc, the total arc, plus the summation of the the normal forces, then times the tangent of phi. So if you have the value of phi, you just take the tangent, then solve it by this one. So it's just very easy solving for the disturbing moment and the resisting moment. Then you have just to divide it, then you have the factor of safety. So you can use this table. So you have this your slice number up to the nth slice. You have the weight of each slice. In here, you have the normal forces. How you can do this? You have the weight. And weight is actually based from your calculation, the unit weight times the area. That's why I did not add a column here, because you just compute the weight directly. So you have the unit weight of the soil, then times it by the area. So you have also the tangential forces. So you have there the weight times the sine of alpha. So what you need here is the sine of alpha. So you have all the summation of the you have here the summation of all the n values and the summation of the tangential forces. Then for the cohesion times delta L, if you have it one by one for slice one like this and slice two like this and so on, it is also the same. But of course, this table, this final formula is similar to this. You just divide this one, but this one is more simple because it is already simplified using a tabulation table. So this summation of the cohesion times delta L. Take note that delta L is actually this is the sum of all the delta L is actually the arc AB. So it is this one. But if you can have this one by one, the length of that arc. So for slice one, so slice two, three, and so on. So factor of safety is equal to the resisting moment divided by the disturbing moment. So we can have it simplified in this equation. You have the C, so from this, the cohesion, you have the tangent phi, which is the angle of internal friction. Then the summation of delta L is actually the arc AB. Then you have the sum of all the normal forces and the sum of all the tangential forces. So that's it. You have already the value of the factor of safety. So here are some of the definitions of those parameters. C is the new unit cohesion. The delta L is the curve length of the slice. That's why if you sum it up, it is the total arc, which is the arc AB. So phi is the angle of internal friction of the soil. So of course, this cohesion, the unit weight, the angle of internal friction will be given to you by by the geotechnical engineers in the company. In in a big project such as the project that we handle in the Middle East and in Africa. My last project with my company is in Morocco, which is also a power plant. So it is part of the Africa. So what we have is we have our own laboratory, and there are different in charge in a concrete laboratory, soil laboratory. So under the quality assurance department. So for us that we are working in the design department, looking into these parameters, sometimes it is complicated to look at it. But if you have all the data coming from those engineers assigned in the laboratory, it's just very easy because you just fill in the parameters. So it is not the same with during the college days that when your professor give you an exam, there are a lot of unknown parameters, and you are going to, before you solve the factor of safety, you are going to solve everything. So from looking into the unit weight, what type of soil, what is given only is the type of soil. You're looking into the cohesion, some other parameters, some other formula of cohesion, and so on. In reality, it the sometimes actually in all of these values are not sometimes, because based on my experience, it's already included in the contract document, which is the technical specifications, wherein all of the parameters are already printed in there. What are the type of materials to be utilized, the approved materials, and of course our laboratory experts, the laboratory engineers will just be re-evaluating those of the values in the technical specifications. So you have the angle of internal friction. You can get it from the laboratory engineers. The summation of n, so of the normal components. So you will compute the summation of t, the tangential components. So AB is the slip surface, which is the sum of all the delta L. So AB, and it is actually, it depends on the angle. This is actually the angle, the angle of that curve. So you can compute AB by having it 2 pi r over 360 degrees times this angle. Okay, so this is now a simple diagram. So we're in this scenario is including now the seepage analysis. If this is the slope surface that you draw, so you have the arc AB. So if you're going to analyze it separately, you will have a partial analysis of the slope. So without having analyzing the seepage. But then it's very also important to analyze it both. In my experience in the preparation of my calculation report, I have it presented in separate analysis. So having it analyzed in terms of slope stability and analyzing only the seepage analysis, but then in the software, because you can clone you will not be doing another model, but you can clone the parent analysis, and you are going to include additional analysis, which is the seepage. So for example, in this case, you already inform, or what's this, what you call that in the software, you already order the software to draw the phreatic line. So it is already the seepage analysis. So when it draws, it actually touches part of the area of your slip surface. So you can see this is already a submerged soil. So therefore, slice 7, although part of 8, a small part is already saturated. So computing now the weight of this slice, say slice number 7, becomes more complicated. Why? Because the upper part of slice 7 is dry soil, but then the lower part of slice 7 is a submerged soil, which is a saturated. So there could be two different areas to be computed for you to compute the total weight. So in here, slice number 2 and 1 seems to be dry. So it's just very easy. You just compute it using the dry unit weight of the soil, or the natural unit weight of the soil. So that's how the analysis works in the software if you're going to combine both of the analysis. So if I will extract one of these slices, this is now the view. So you have the volume or the area on the top part of the phreatic line, and the lower area or volume or below the phreatic line. So of course the software will be doing the analysis in it. So here are the table. Here is the table and values of finding the location of the center of the critical circle. So it is based on the slope. So if the slope is 1 is to 1, take note this is again horizontal is to vertical. So if it is 1 is to 1, alpha 1 is 27.5 degrees and alpha 2 is 37 degrees. So for 2 is to 1, or what we know here the films as 1 is to 2, 1 is to 3, 1 is to 4, 1 is to 5, they have the same directional angles in finding the center of critical circle. So the center of that circle, because as mentioned, it is just an assumption. But then we have to locate which is the correct assumption point. So in here, from only 1 is to 1 is different. The rest have the same alpha 1 25 and alpha 2 is 35. So where are we going to utilize this one? So in here, if you draw now manually the cross section, you have here that 2. What you're going to measure is the height of the dam. So from that edge, you draw an imaginary line from that 2, which is equal to the value of h going down. Then draw going to the left a value of 4.5 times that h. So you have that one. So you have point Q. So have it is there. So if you can see, you have the alpha here based on the slope. So that's why if you go back to the previous slide, if that is the slope 1 is to 1, so you are going to use alpha 1, 27.5 and alpha 2, 37. Where is that alpha 1 and alpha 2? So this one is alpha 1. If this is 1 is to 1, if the slope is 1 is to 1, you are going to draw manually the alpha 1, which is 27.5, and draw a line to that of the 27.5 degrees. Then on the crest, you draw a horizontal line, extend it, then draw the alpha 2. So what is the value of alpha 2? It is 37. So I'll measure 37, then click in here. The intersection of those lines of alpha 1 and alpha 2, you can go also draw this from point Q to that point. So that intersection is actually the center of the circle, which is this intersection. So that is the assumed one. So center of critical slip surface will lie at some point on line PQ. So it is somewhere here. Although you can have it first at point P, but it can be in the software, it can analyze those the different points because it is okay, because the software can handle even thousands of iterations, thousands of repetitions, so it is okay with that of the software. But of course, if it is for manual calculation in the classroom, the instruction is always at this point P, have it the first iteration or first try. So you are going to have to draw it, and of course, because it is a manual or graphical calculation, I'll draw a circle from this point P to the 2, and that becomes now my radius. So if I'll draw now the curve, so all that touches the body of the dam will become part of the critical slip surface. Okay, so actually it is a very simple. So same as true with that of the upstream slope. If you are going to draw, so the same measure h, then going to the right 4.5 h, then measure alpha 1, then you are going to measure also alpha 2. Then measuring those values, then extend all the lines, and you have there the intersection of the different lines, which is point P. So from point P to Q, you draw that extension of the line. So with that of the line, the center of the slip surface may lie. Okay, so from point P up to that of the extension. So here is one. I cropped this one because I already mentioned it, because it could be part of the assumption that if the values is very small for the tan for the angle of internal friction, which is from 0 to 15, which is the phi. So the critical arc passes the 2. So of the slope, if the inclination of the slope is less than 53 degrees. So there are a lot of assumptions, not only this one, but it is just an applicable assumption if you're going to draw it manually. or the graphical manual presentation or analysis, because of course it's very hard, but the software will have to do it by its own. So it is not that difficult to assume, because the the software will assume different points, will assume different slices, and will compute the different values of the factor of safety, and it will give you the most critical factor of safety, because we are looking here the most critical, not the best, or the factor of safety that is always passing the criteria, but it will give you the critical or the smallest possible value. So I will not be having a discussion of this example. I just show how I gave problems to my students in terms of the stability. So of course you are going to give them the line, the drawing of the C-pace or the phreatic line, the dimension. If you're going to include filters or filter drains, and that one, the slope, everything. So based on that, so they are going to draw the point or the center, so the edge, because the height of the dam is 22, so you have it there. So that is the process of how you're going to compute. Then this is another method, because you're going to compute y1, y2, the different height of the slip surface and so on. Or you can also use the tabulation, the one I presented here. It is actually more simple, but this one is just another method of computing the n value using the diagrams and the t values. So this one, so the t diagram. So solving it, it is the same. You have the cohesion, the arc, and so on. So, and it turns out that the factor of safety is 1.64, and based on the accepted practices in construction in terms of slope stability, it is 1.5, which is also, if you still remember, during the hydraulics, it is always compared to that of the 1.5. So that is a 50% additional to that of the 1.0, which is the exact value of the forces acting on the dam. So why it is very, very high? Because it is hydraulic structures, and it is, we are talking here of the pressure of water and the behavior of the soil. So in some other cases, we use 1.25 as the limit of the factor of safety, but is for that is for temporary structures. So for example, in the dry dock and shipyard that we construct in the Sultanate of Oman, I designed their coffer dams, which are temporary. It is only for 3 to 4 months during the excavation of the dry dock foundation in the sea area. Of course, you are going to block the seawater that will go inside the excavation area. So what we are going to do is we construct coffer dam all throughout around surrounding the area, which is a semicircle plot in that, if you're going to look at it in the top view. So what we did, because it is just temporary, after 4 months we are going to demolish the coffer dam, so we use only 1.25, because of course going into this value of 1.5, it has a cost impact. So if it fails, for example, this one 1.64, so meaning our slope and the properties of the soil, because it the failure of the factor of safety is based on the slope and the material properties. So that is only the two factors that should be considered. So this one is 1.64, meaning it is all safe. So the material is good, the slope is okay. But then there are cases that, for example, the one of the actual case that I have during the time that I work there. For example, I got a value of factor of safety of 1.64. For me, as the designer of that coffer dam, my analysis is it is very okay, because it is very safe, because it exceeds even 1.5. So I will approve my calculation, the calculation of the team. Of course, it is not done by myself alone. It is an effort of a team, of the whole department, of the whole design department. Then we have to present it to our design manager, and he will analyze, he will approve. And based on this 1.64, of course he will approve, because the calculation is more than that of the limitation. So it means that the structure has its structural stability. But of course, in the actual project, it is not only up to the level of your manager in the design department. Although if you are going to submit our calculation to the engineer and to the owner, they will just approve it because it passes. That they will only look into is that the parameters are all set, and based on the calculation, it passes with that of the criteria. But then a copy of this calculation, not the whole of the calculation, but this factor of safety, because you are going to do, once it is approved, they are going to do the cost analysis in the commercial department. If the commercial department in that department, if they saw this 1.64, they will be rejecting it, and they will be having comment to revise the calculation, and you are going to revise it using a value of factor of safety which is 1.5. And that is now the most difficult part in terms of the design analysis. Why? Because you are now going, actually you have to do it using backtracking analysis. You have the value 1.5. So you are now going to look into, because here the materials are already, for example, the materials has been already delivered. So meaning you cannot change the cohesion, you cannot change the unit weight, and you cannot change the angle of internal friction, which are the input parameters for the more column analysis. So what is the only parameter that you can change, that you have control? It is actually the slope. So I can change the slope so that this factor of safety will become 1.5. So there are a lot of simulation, there are a lot of trials and so on. One good thing is in the software, once you reduce the slope, it's just very easy. So in one overnight, so for example, from we do it over time, so from 6 p.m. by 9 p.m. we have it already presented, we have it printed, and everything are all set. In which the 1.64 factor of safety has been changed to 1.5, which is the exact limit. Okay, so will not be having this problem. So, but this is our sample solution. So using the table that I presented, which is I think the most easiest way of solving the factor of safety. Then you have the FS value, then 1.55, so it is safe. So that's it for the slope stability analysis, and I hope you get some review points in terms of the use of the method of slices, how it is being calculated, how it is being analyzed, so that we can proceed with that of the introduction to the software and to that of the simulation analysis.